Good afternoon from me as well. So I will first present all the papers together shortly, not to jump in between. And then each presenter will have 15 minutes of time to present their work, and then 5 minutes will be reserved for any questions. So I'll be keeping the time. When you have 2 minutes remaining, I will lift my hand with 2 fingers. And when your time is up, I will stand up and try to look intimidating. So let's go now through the papers. The first one is Mobility Policy Proposal Using Machine Learning Techniques by Miljana Šulajkovska and colleagues. Then we have Vehicle Axle Distance Detection from Time Series Signals Using Machine Learning by David Susic and colleagues. Then we have peak detection for classification of number of axes, so axles. So again, probably a similar application domain by Žiga Kolar and colleagues. Then we have a prediction of the inflow of Macedonian hydropower plant, a topic which is, I think, more and more interesting every day, I'm afraid, by Emilia Kijevska and colleagues. Then we have IMF quality assurance of mammograms using deep convolutional neural networks and transfer learning from medical domain by Gaspar Slapničar and colleagues. And finally, we'll have an online presentation, learning the probabilities in probabilistic context-free grammars for arithmetical expressions from equation formula by Maria Čaušovska and her colleagues, actually. So I now invite the first presenter to take the floor and present the work. Thank you. It's important.
Yeah, I need to share.
Yeah, it's shared. So it's okay. Yeah.
Okay, so hi everyone, I'm Šulajkovska, and today I will present our work about urban mobility policy proposal using machine learning techniques. So here is the outline of the presentation. First, I will describe the problem. Then I will give some brief introduction to the UrbanNet approach. Then I will talk about the data collection process. After that, the machine learning algorithms that we apply on the data. And finally, I will discuss the results and conclude the presentation with the work. So let's start. According to the United Nations population estimation, the total population will reach 9 billion people by 2050, which means that it will increase by 80%. And this will have great impact on the transportation system in metropolitan areas, as most of the people are moving from smaller places to big cities. And that's why the city authorities are trying to meet the people's needs by testing and evaluating different mobility policies. So they simulate different mobility policies, and also an expert knowledge is required to evaluate those policies. But we need to test a lot of different scenarios, which is time-consuming and power-consuming. And here our goal is to propose mobility policies automatically using machine learning techniques. As part of UrbanNet project, which is about decision-making in urban transportation field, we develop a machine learning module where the main objective is to have one simulation run as one training example, and we tested the approach on data related to the Bilbao city in Spain. So here we have a general overview of the UrbanNet approach. We have developed a couple of modules. So the main idea behind UrbanNet is to build an intelligent platform that will help decision makers making better decisions. So we have the traffic simulation engine, the support system recommendation engine, the data platform, and we have also tools for visualization. And here we can have a closer look of the machine learning module inside the Urbanic system. So we have the microscopic traffic simulator as the central part of the machine learning module. It is used to simulate different mobility policies, and as input it requires some data which is related to the network, the public transport data, the travel demand, and the mobility policy we want to simulate. So the mobility policy can be related to some changes to the network, such as adding a new road or closing some street for private transport and so on. We can change the public transport schedules, the travel demand, and so on. So once we run the simulator, we can get some data, which is used then to calculate some KPIs, and altogether is used to train the machine learning algorithms. So the machine learning module takes as input the desired city changes, while outputs the mobility policy that satisfies those requirements. So, for example, if a decision maker is interested in reducing the CO2 for 5% and increase the public transport usage for 3%, the machine learning module will take this as input and it will output the appropriate policy that satisfies. So, as I said, to collect the data, we used a microscopic traffic simulation tool. We have tested a couple of state-of-the-art solutions, but we have chosen MedSim, which is a multi-agent traffic simulation. So it is used for microscopic traffic modeling, which, contrary to a microscopic simulation, we simulate every vehicle separately. So this enables us to analyze traffic flows, congestions, public transport, bicycles, and so on. The core concept behind the simulator is in the coevolutionary optimization, where every agent has its own plan. The plan is simulated and it is optimized separately on the network until some equilibrium state is reached. And if we take a closer look how the simulator works, we can see that several input files are required, such as related to the city model, the traffic and population data. So first, and here on this picture, we can see the flow of the simulator. So the simulation is optimized by configurable number of iterations. All starts with initial demand that contains daily plans of the people's movement. So those plans are simulated by the MobSim module. So each plan then is scored and, if needed, is modified by the retaining module. After the simulation is done, we can analyze the data from the simulator, which is in the form of event files, travel distance statistics, and so on. And all these files then are used to compute the features for the machine learning module and also to define the target variables. Okay, so in order to collect data, we need to simulate a lot of different scenarios. We have only one mobility policy, which is related to closing of Moya Square in the city center of Bilbao. And in order to make many scenarios, we did 40 different variations, which are related to changing the start hour and the duration of the closure. And here on those two bar plots, we can see the results of the simulations. So on both plots, on the x-axis, we have the time of closure, while on the y-axis, we have duration. On the left plot, the z-axis depicts the CO2 emissions, while the z-axis on the right plot depicts public transport usage. Both values are in percent, scaled according to the baseline scenario. So, in terms of reducing the CO2 emissions, the best scenario is if we close the square from 9 in the morning for 1 hour. In that way, we will reduce the CO2 by 1%. But on the other hand, if we close the square in the afternoon, in the peak hours here, That's from 5 p.m. The city has congestion in the surrounding areas, and the overall CO2 emissions get increased by 26%, even though the public transport usage has increased and the car usage has decreased. So what scenario will be selected depends on the goal that the city wants to accomplish. Therefore, in order to select the best options is very hard if only human knowledge is included. That's why we want to apply some machine learning techniques. So from these results, this data we use to compute the input data and target variables for the machine learning module. So the input features are represented with some KPIs, which are predefined by the users or the city authorities, and they're related to air pollution, mode usage, bike safety, and bikeability. So bike safety is computed in the way that if the cyclist ride on a cycle path is more safety than riding on a road that is shared with cars and buses. And the bikeability is related to the score of the bicycle infrastructure. And the target variables are representing the mobility policy. Here we can see on this table, the target variables are represented with start time of closure and duration of closure. And both variables are discretized. The first is discretized in 30 minutes interval, while the second is discretized in 15 minutes intervals. And once we have the data, we can apply some machine learning methods. Because here we have a multi-output regression problem. Not every algorithm supports multi-output regression, so there are ones that supports and the other that doesn't support, we did a proper multi-output regression. So to evaluate all of them, we use cross-validation technique, and as an evaluation metric, we used mean absolute error. Here in this table, we can see the results from the multi-output regression algorithms, the Hartley multi-output regression algorithm. And we can see that k nearest neighbors proved best results, let's say, with mean value of mean absolute error of 3.7, which means that the difference between the predicted and the true value is approximately 4 time intervals, or 2 hours for the start hour and 1 hour for the duration. And here on this plot, we can see the true versus predicted values when k nearest neighbors is applied. And finally, to conclude the presentation, we showed how machine learning techniques can be used in mobility policy proposal. So machine learning can learn from the output of the simulation, and that helps us to simulate only a limited number of scenarios, not each of them. And also, this approach can help decision makers when they're confronted with complex systems. So for future work, now we are expanding the dataset in a way that we close the surrounding areas of Moyoa, and we have like many different combinations. So by doing so, we can add more target variables, which are related to which area to close, the length of the street to close, and so on. And additionally, in future, we can include a mobility expert to validate those results. Thank you.
Thank you very much. Any questions? Yes.
So how exactly do you calculate the CO2 emissions?
So the simulator, the MATSIM simulator, provides additional packages for calculating different KPIs. So to calculate the CO2 emissions, we used HBFA book of factors for emissions that each car, like every different type of car emits differently. So we use those factors. We also consider the gradient of the road. And when calculating the CO2 emissions, we consider cold and warm emissions. So the warm, I think, are exhausts when the engine starts, while the code are exhaust when the car drives, or it's
So this is in case the cars are not moving.
yeah, when they're not moving, but the engine is working, like they also like it means so.
We had another question.
Yeah, so my question relates to the evolutionary computation part of this work. At some point you mentioned that co-evolution is used for the agents to calculate something.
Yeah.
Now, okay, so co-evolutionary approach is usually done in such a way that population of agents is divided into subpopulations that are solving some sub-problems and then cooperate together to solve the entire problem. How is this done in this case? What are the sub-problems that are being solved?
To be honest, we didn't develop that part of the work because this is done by the simulator. So,
Who developed this simulator then?
sorry?
Who developed this?
This is developed by Eta Hatsirik and Tube. So we use like already developed simulator.
I would like to understand a bit better how this system would be used in practice. So if I understand correctly, for each, let's say, question that you want answered, you have to generate data through simulation, and then you search the space of possible, I don't know, KPI values, looking for the best ones, or how does it work?
Like we do not know the output of the simulation. So we suppose let's close some areas and then we can see the output of the simulation, and then we calculate the KPIs. But this is with the machine learning will be reversed because we input the KPIs. For example, we want to accomplish some goal in the city, and then without simulating, we can get like the desired city change we want.
So let's say I want to reduce CO2.
Okay.
I have to first come up with the idea to close something or do something else.
Yeah, you have like limited set of solutions. Mm-hmm. Like for example, now we are adding to close many parts around the city center, and if we simulate like every possible combination, there are like thousands of simulations. And if we simulate 1,000 simulations, it will take us like 3 months maybe. And that's why we only take 200, for example, simulations. And that's why we train the machine learning model. And there is no need to simulate the others because we don't know the output.
But so you can make it, I mean, here you said that you can change the start and duration.
Yeah.
But you can also change the place that you close.
That's in the future work, yeah. So far, it's only the start and the duration. But now we computed also simulation that considers an area to close on.
I had one question in regards to the 3D graphs. I think they're on slide 8. You can open them. Yeah, here. So for the left one, I was curious because these two bars, basically that are higher than everything else, these are closures at, I don't know, somewhere between 3 and 6 p.m., I guess, and they're of duration of, let's say,
1 hour?
Yeah, 1 to 2 hours.
Okay.
But then if you close it for like 3 hours, it drops extremely low. Like the CO2 just drops to like 0. So do you have like an interpretation why this happens if the duration of closure is 1 hour more, it just drops extremely low?
I think that agents can learn like, because these are separate simulations. And they're stochastic, and like every simulation, it works by its own. So, like, I hope that agents learn that it will be closed for so long, and they. But.
Wait, so what you're saying is that because it's closed for longer, it has more time to learn than it's closed for longer?
I think so, because they're stuck before the closing street. and they can move around them.
It is strange because one would expect that 3 hours is the same as 2 hours plus.
Yeah, I would expect a gradual decrease.
Yeah, so all the bad things that happen in the first 2 hours should happen when you close for 3 hours too.
Okay.
Okay, it seems that there is a lot of debate for the break in the corridors, and I suggest that we thank the speaker again.
Okay, hello everyone. I will present a paper with the title Vehicle Axle Distance Detection from Time Series Signals using Machine Learning. So, let's first take a look at this image. I'll use this to explain the motivation behind this paper. So we have an example of damaged road due to override. So this damage that we can see was caused due to too many vehicles that were overweight passing this road. So in order to reduce the damages and also to catch the vehicles that are causing the damage, we have to detect vehicle weights. So in this paper, we use data from sensors that are placed under such bridge, and they record time series signals with vibration signals of the bridge. So in order to accurately measure the vehicle weight, we have to determine first 3 things. So the first one is vehicle speed, the number of vehicle axles, and the axle in between distances. And so, as it turns out, the first 2 are fairly simple to determine, while the third one is not so trivial. And I will explain in the following slides why this is not so easy to do. And this is also the story behind this paper. So we compared 2 methods for detection of axle distances, so the calculation of the actual axle distances. The first one is the signal decomposition approach, and the second one is convolutional neural network autoencoder approach. Now, we do not have the actual ground truth for our data, but we use expert model as our ground truth. So the experts that work in this field ran their model on the same data set, and we use their results as our ground truth. Okay, so we use, so here we see the configuration of sensors that are placed on the bridge. There are 8 of them, 8 identical sensors. And immediately we see that the sensor 1 and 2 are placed in the separate columns, and they are used to calculate the vehicle speed. And vehicle speed is calculated by overlapping the signals using the cross correlation method. Our dataset includes around 60,000 vehicles, so each instance is the 8 sensors. Here is the example of a vehicle with 5 axes. The peaks correspond to the vehicle axis, and the amplitude corresponds to the weight of the vehicle on that axis. So now, crucial thing here is that we cannot directly calculate the exit distances just by looking at those peaks, because what happens is that due to the interference of the signals between individual axes, the peaks may shift. And so this effect can be seen here when the three axes are very close to each other. The left and the right are shifted apart. And here's the animation, how this happens. So the green line represents individual axes, and the black line is the raw data, so the signal that sensor detects. And we see this in the cases when the axes are very close, the peaks of the sun signals shift inwards. And so the important thing is to, when determining the axis distances, is to detect this shift. Okay, so the first approach is signal decomposition approach. This is also includes two steps. The first one is determining the most appropriate signal. As I said, there are 8 signals for each vehicle. And so for this purpose, a matrix was constructed. So for each instance, we have, so the dimensions are the number of instances times the number of sensors for each instance. And each entry represents the number of peaks detected using a simple peak detection algorithm that just calculates the first and the second derivatives. And so we trained a few models here. The first one is the regression model. This one predicted the number of peaks using this using the calculated peaks from each signal. So for the training, we use the actual peaks, the actual number of peaks. And then we also trained classifiers for each of the sensors. And the classifier output was probability that the calculated number of peaks is correct. So how we determine the best signal? First, for each instance, let's take instance 1, we predicted the number of peaks rounded to nearest integer. And then we iterated through all of the signals, starting with signal number 1, and we checked if the number of detected peaks matches the one on the regression output. And if so, we checked if the probability of the classifier that this number of peaks is correct is above a certain confidence threshold. Now, in theory, we could miss the, we take the first one that meets the criteria. So in theory, we could select a signal that is not optimal. However, in practice, we found that more than 80% of the cases, signal 1 is actually the best. So that's why we stuck with this approach. And the second step is the composition of the signal. The composition was done with so-called base waves. These were the functions that were meant to represent isolated axis, so how the signal would be from one axis only, and it can be defined with 3 parameters: the x location and the x and y scaling. And this decomposition can be defined as an optimization problem where we want to minimize the distance between the original signal and the sum of the base waves. And here we can see the decomposed signal with the green lines. And now in this case, we use the peaks of the base waves for the calculation of extra distances. And it's not quite obvious, but we can see that the base wave peaks slightly shifted. So this is how we capture this peak shift. The next approach was convolutional autoencoder. This is the structure. It consists of encoder and decoder. In this case, we always selected signal 1 as the input. So encoder has 3 convolutional layers, each followed by batch normalization and max pooling. While the decoder has the same structure reversed, but the max pooling layers are swapped with upsampling layers. So in this case, the input is the raw signal, and the output is array of zeros and ones, where ones denote the positions in the signal where the peaks are. So here with green, we see example output. We see that most of the values are 0 or close to 0, but some of them are not, and those represent the probabilities that there is a peak there at that sample, at that time step. And so after the decomposition, we defined 2 thresholds, T1 and T2. So in order for a peak to be considered a peak, it had to have a probability of at least T1, and in order for a signal to be processed, the probability of the highest peak had to be at least T2. And so if these criteria were not met, the instance was skipped. And this is similar as in the composition. If these criteria were not met, the instance was skipped as well. So this is the option that we gave ourselves. So if we're not too confident in our prediction, we can skip it. Okay, so here are the results. We see the first signal decomposition approach. So here is the confidence threshold and the percentage of, or fraction of skipped instances, and the 3 accuracies. And so we see in the bracket, we see plus minus some percentage. And this percentage means that our prediction was considered as true if all of the exit distances were within, in this case, 2% of the ground truth, or within the, as predicted by the expert model. And so, of course, we see that if we increase this margin, the accuracy increases. And for the autoencoder approach, this is similar, but here is the T2 threshold, the fraction of skipped instances, and again the accuracies, and we see that they are quite higher. We see that let's say 15, 20, 25% of the skipped instances, the accuracies already reach 96%, which is much higher than, around 10% higher than the composition approach. Okay, so to conclude my presentation, we tested 2 approaches for the calculation of exit distances. We used data set of approximately 60,000 vehicles, and we compared our results with the ones as calculated by the expert model. We also found that the autoencoder works significantly better than the signal decomposition approach. And now for the future work, we will calculate the actual vehicle weights, which is the motivation behind all this. Okay, so thank you for the attention. Some time for questions.
So I'm wondering about the ground truth. You said that it's based on an expert model. So your model can't be better than this expert model, or if it is better, you will not know it. And presumably the expert model is available and can be used. So what's the point of building another one that approximates the expert model?
Well, okay, thank you for the very good question. The story behind the expert model is that it is not only the expert model. The experts first use their model, and then they, using some heuristics, they corrected some of their data. Around 5% of the data is corrected. So in theory, if we reach 100%, it means that we, or above 95, it means that our results should be better than the experts model. But we cannot know this because the actual ground truth is unknown, both to us and to the experts.
And these heuristics cannot be simulated as well? I mean, simulated. I don't know what they are. Do they require an expert looking at the data, or
Yes,
they could be applied?
and the images. Because there was a camera next to the bridge, and it was also used as a helper to determine if some results needed correction or not.
Do you use that camera?
No. We don't have access to the data. We're not allowed to use it.
So it looks like your signals are very clean and nice. I'm guessing that you did a lot of some sort of smoothing or removal of noise or something like that.
Actually, these are raw signals. But I agree they're very nice, yes. We were given the nicest possible data set available. Because they use some other bridges as well, and supposedly these are the cleanest signals.
Do you have any interpretation of why the encoder works better than signal decomposition?
We think it's because it's neural network. It's a good question. I don't know some actual answer. It's more sophisticated than the decomposition approach, because the composition uses 10 parameters, a lot more.
Any other question? Okay, we heard some good questions and interesting answers. Let's thank the speaker again. Thank you.
Hello, today I will present you peak detection for classification of number of axons. Peak detection is a common requirement in scientific data processing because peaks are useful topological features of time series data. For example, in financial data, peaks indicate abrupt rise in price or in volume. Peak detection is also used in many other areas, such as bioinformatics, signal processing, image processing, and spectrometry. Peak detection can also be used for classification of number of axles for vehicles. For example, each peak represents one vehicle axle. And peak is detected when a vehicle places one of its tires on a weight sensor. Together we had 16 sensors, but only the first one was selected because it produced the best result. On this figure, we can see a signal which has two peaks. Peaks are marked with orange cross, and our objective was to detect how many peaks there are in a given signal, and in this case, 2. Each machine learning method used 62,000 samples. Each signal had a different length, which was a problem. So we had to pre-process by determining the maximum signal length, and then every other signal that had length less than the maximum signal length were added additional zeros until the end. So here is the first method with artificial neural network. On input, it was given a whole signal. It had 2 hidden dense layers, and on output, softmax activation function. It reached 91% accuracy. Second method was peak detection with convolutional neural network, the same as in the previous case. The input layer was the whole signal. It had 2 convolutional 1D layers and 2 max pooling 1D layers, and at the end 1 dense layer and an output layer with the softmax activation function. This method reached 97% accuracy, but it reached even higher, 91% accuracy, if we decided to skip 6% of samples. We also tried the method with the autoencoder, which David already presented, and the method with autoencoder, which also uses the convolutional neural network, also produced a similar result. Next, we have peak detection with predefined method find peaks. This method finds all local maxima by simple comparison of neighboring values. Peaks are samples whose 2 direct neighbors have a smaller amplitude. The problem here was that the height was different from sample to sample. What is actually a height? Height is a minimum required height for peaks to be detected. So every sample had the different height, so we needed some kind of formula to adjust this height to every possible sample of the data. This method reached 89% accuracy. Next, we have peak detection with library TS-Fresh. It's a Python package, actually, which automatically calculates a larger number of time series characteristics, so-called features. Once those features were generated, we used gradient boost classifier to produce the results. And this method produced 89% accuracy. So to sum everything up, the convolutional neural network produced the best result, and they all outperformed the traditional machine learning algorithms. And these results can be improved with different parameters. With optimizing the parameters, we can use different learning rate, different number of neurons, different activation function, etc. We can also try by changing the architecture of the neural network. We can maybe increase the number of hidden layer or increase the number of convolutional 1D layers or something else. And the results of this study can also be extended into determining the axle distance. Thank you. That would be all.
You have quite some time for questions.
I have 2 quick questions. One is, do you know what type of peak detection TS-Fresh uses basically for themselves? Do they implement it on their own, or do they use something like find peaks in background? Because I saw the accuracy was exactly the same. So it might be that they use just find peaks for themselves as well.
They use find peaks and convolutional neural networks, both.
Okay, that's one question. The other one is, you achieved higher accuracy when removing 6.5% of samples. Which samples did you remove in those cases? Is there some logic, or is it just those that didn't work out?
So you mean those samples that were skipped?
Yeah.
Those samples were skipped because the probability for this sample was below the given threshold. So, for example, if the sample had probability 95% accuracy, and if the threshold was 90% accurate, it wasn't skipped. But if the sample had like 50% of probability and the threshold was 90% probability, it was skipped. So this was the method for skipping the samples. The probability was the method.
I have another question about, seems like for this time series type of things, people commonly use some of the recurrent neural networks. Have you maybe tried or considered using either gated recurrent units or LSTM, so long short-term memory units?
No, we didn't try that, but it's a good idea maybe for future work. Thanks.
So it seems that this work and the previous paper are dealing with the same problem because they are strikingly similar. But I would like to understand the relation between one and the other thing, because I think what David was presenting was also somehow about detecting these peaks.
Yes, that's correct. The autoencoder can be used to predict the number of peaks and to predict the distance, the axle distance. So it can be used for both. While these methods that I presented were used just for predicting the axles, the number of axles.
Okay. And then I would like to understand how you define accuracy here, because I mean, you have these peaks, you can of course detect them or not, but also, I mean, you can detect them in exactly the right place or not. So how is this accuracy to be interpreted?
The accuracy was calculated by the number of correctly predicted peaks divided by the number of all predictions.
So a correct prediction is if there is a peak in the ground truth and yours is in exactly the same spot, not one sample left or right.
Yes, that's right. We assume that their data is the ground truth. So yeah, it was based on that.
Also, two quick questions. So you mentioned that your future work will also include dealing with different topologies of the neural network. But the one that you showed to us, how this one was determined? Did you somehow put it together, or is it some predefined topology?
We tried 2 or 3 different architectures, and this one provided to be the best. We didn't try many different architectures, just this one, and maybe it was luck. I don't know, really.
And regarding the results, so like in the previous case, it turns out the neural nets are the best for this problem. So do you have any explanation other than this is because these are neural nets? Any deeper explanation why this is?
Because the neural networks work like human brain. So if human can detect peaks easily, then so can the neural network.
Okay, well, it depends. But just as a comment, if you compare or you emphasize the strength of modern computational techniques, sometimes in the literature you read, okay, neural nets are really good, but evolutionary computation is even better because evolution gave us human brain. So philosophical.
Okay.
Just to know.
Any other questions?
I also was wondering if the comparison was fair, because the neural networks have different layers, and perhaps one layer serves as like signal smoothing and so on, whereas the find peaks method was fairly dumb, I would say. It was just without any smoothing of the signal. That's how I understood it. Am I correct?
Yes.
So I was wondering if you considered any like non-neural network method, which would be a bit more sophisticated, maybe with some signal pre-processing, at least the moving average or something like that, and then comparing that to neural network, because there is quite a wide gap between the complexity of your find peaks method and then the neural network.
Yes, we tried the method with calculating the different derivatives, and it proved to be also good.
And did you use any signal preprocessing for that?
No.
If not, I have one, although there are many, but we had some time. Because of this last question, I really have to ask. So, okay, some methods are simpler, some are more complicated. We can debate whether it's fair to compare them or not. I mean, whose fault it is that some method is simple. But what would be interesting maybe in this respect is comparison of the runtime. Do you have any idea? I mean, I don't know whether you have this in the paper. It would surely be interesting to have runtimes. But do you have any idea like this, any feeling what takes them and what are, let's say, the differences?
The convolutional neural network worked 2 hours for learning phase, and the find methods was instant. Find peaks, sorry.
Yeah, so this might be also an interesting result if you would measure this in the report. It might be quite relevant in some applications. So,
yeah, I agree.
Thank you. Any other questions? If not, thank you very much. Thank you.
Okay. I am Slovenska, and I will present the prediction of the inflow in Macedonian hydropower plants using machine learning. Somehow, because I don't see the presentation here, I have to stay like this. Okay, so this research was part of a bigger project under ESM, which means Power Plants of North Macedonia. How ESM manage electricity production and electricity consumption. We work at the part of electricity production, but actually first we obtain how the amount of electricity consumption on daily, weekly, monthly, and hourly basis. Then they consider how they will manage the amounts of electricity production on the same basis. The main power suppliers are the thermal power plants. And after considering how the amount of electricity production, like how much of the electricity production they can supply, after that they consider how much of that they can sell or they should buy. Where there are some energy exchange as SKUI, for instance, Hungarian derivative energy exchange. But there are also peaks on daily basis. For instance, in the morning, during the period when the people are waking up, or I don't know, during the lunchtime or at night, for instance, when the people are turning on most of the devices, also lights and everything. And those peaks are covered actually by hydropower plants. So hydropower plants are not the main suppliers, but they are used to cover the peaks during the days. The importance of predicting the amount of water accumulation is not just for just to cover the peaks, but also to prevent lake overflow, because there are people who live around the lakes, and also public spending. Why public spending? Because the earlier you buy the electricity, the cheaper it is. And opposite, the later you buy, the more expensive it is. So for instance, if they buy electricity, if they know the amount of electricity they need, and if they buy it like 1 week ago and 1 hour ago, the difference is big. Now we would ask, like, why do we use machine learning and everything to predict the inflow? It is pretty straightforward. Like, the amount of precipitation is the amount of the inflow. But it's not that easy. Actually, the complexity of predicting the amount of water accumulation is because of different types of plants. There are three main types of power plants: pump, storage, run-of-river, and storage. For instance, in run-of-river hydropower plants, we need only the precipitation in that hour, or maybe a couple of hours before that. Why? Because the rain goes directly to the river. But for instance, for storage hydropower plants, it's not like that, because the water of the rains is conducted all over around the hydropower plant, and it's conducted by pipes into the hydropower plant basin. Also, another thing why it is also complex to predict is different landscapes, different climatology. For instance, the dryness of the place around the river is different for each river, or also for the basins, because, as I said, it is conducted by pipes all over around. And geology. Geology is the types of the soil around the hydropower plants. So what did we do? This is a process. We collected the data for hydropower plants and weather station. It's actually meteorological stations. The data was tabular. Collected data, we processed it, we applied some machine learning. After that, we analyzed the results, and we developed models for how we can monitor the inflow into hydropower plants. This is the equation we used because the obtained data for hydropower plants was represented in watt hours. So this equation is represented how actually the inflow Q, from inflow it is calculated to energy. Here we have the data sets. At the beginning, we had only the amount of electricity production represented in megawatt hours, as I said, and daily amount of precipitation represented in liters. As I said, the data was tabular, and it was during 10 years, from 2009 till 2019. So we had 10 years on daily basis, tabular data, and only two features. The first one is the feature we used as descriptive space. Actually, this was the input, and the amount of electricity is production is actually the feature that we should predict. This was the output. At the beginning, the models that we developed were pretty bad. The results were pretty bad because we had only one feature, and it's not that straightforward as I said. Then what we did, I will explain later actually how we handle the data to obtain better results. Because missing values were less than 1% of the total data set, we filled out it using the average of each feature's values. For one of the hydropower plants, because we were working on the biggest 5 hydropower plants in the Republic of North Macedonia, for one of them, we obtained even more features. For instance, humidity, cloud cover, temperature, the intensity of the precipitations, and etc., etc. They are missing values in the additional features I counted now are filled in with the average of the instances that have the same value in the most meteorologically related feature. What does it mean? This means, for instance, cloud cover and humidity. They are meteorologically related. And what we did, at the features of missing values in cloud cover, we filled in with the average of the instances that have the same value in the humidity feature. Because, as I said, for the rest of the hydropower plants, we had only one feature. We derived 19 new features. as minimum, maximum, average, variance, p-variance from the last 5 days for both main features we have. Also, the time we split it and we calculate sine and cosine functions because, for instance, 31st of January is really close to 31st of December is really close to 1st of January, but for the model, it is pretty different. 31 and 1. That's why we applied some trigonometrical functions. This is the correlation matrix. Why I put it here? From the correlation matrix, we can see actually that the most related features to the outcome or to the output or the prediction of the inflow are the features from the 5 previous days of all these derived features from the 5 previous days of both main features. After that, we applied some machine standard regression models, like support vector machine, random forest, linear regression, gradient boosting, extreme gradient boosting, lasso, nearest neighbors, decision tree. Dummy predicts the mean of the target values for each instance. We used evaluation matrices, mean absolute error, mean squared error, root mean squared error, R squared. And after that, we tried an we experimented with selecting k-best class. This is a class from sklearn. We tried to see how we will obtain the best result. If we use the best 5 features, the best 10 features, 15 or 20 at all. The second one, this graph is actually from the hydropower plant that we had more features as cloud cover, humidity, and temperature, etc., etc. That's why we have different numbers. And we concluded that actually the results for each algorithm were almost the same, or the best results we obtained using all the features. So it's the best to use all the features if we want to obtain the best results. Each feature influences a bit more or less to improve the accuracy of the models or to reduce the error. I use hydropower plant of Barabin here just to see the table, how the results were looking alike. The average absolute error we obtained was around 80% of the average daily inflow. There is a graph of the actual versus predicted values. As we can see from the graph, they are pretty covered from each other. 8 different machine learning models. Best results are obtained, although we use 8 different machine learning models. Even though at the beginning it's not part of the paper, but we also tried neural networks and some higher level of processing the data. But however, it seems that this problem is from linear nature. So the best results were obtained by linear regression and gradient boosting. The worst on dummy, as I said, it is the mean of the target values. We concluded that the most important factors are inflow-related elements from the preceding days. As I said, not just from the correlation matrix, but also after that from using the feature importance of different algorithms. It is the derived features about last days. That's how we obtain better results. Why it is like it? Because it takes a certain amount of time to reach the Bazen's SN inflow. As I said, firstly, the rain shouldn't be just rain. It can be also hail or snow. Also the dryness of the soil around the rivers. Also the temperature. It is different if the temperature is higher or lower, because if it's higher, the water is conducted faster to the rivers. And also the snow is melted faster. Continuity in the data. we confirm that for time series it works the best if you use continuity. What do I mean by this? For instance, because I need the previous 5 days. Why I need the previous 5 days? To calculate the minimum, maximum, as I said, average, variance, and etc. Run-of-river diversion hydropower plants, the rains are accumulated immediately, as I said, and as a main conclusion here, we can say that the precision of projected water condition is the key drawback for obtaining even lower errors. The more accurate the weather conditions are, and the longer the period of time of projected weather condition is, the better the prediction of inflow in the hydroelectric basins will be. General model couldn't be developed because only hydropower plant dependent models can be developed because of different types of hydropower plants. As I said, this is run-of-river, this is storage. This is the main storage hydropower plant in Macedonia. It's called Mavrovo, and the water is conducted all over around to the artificial lake. Geological properties of temperature fluctuations in the past, etc., etc. Future work. Predictive models, as far as possible in the future, will be better and better. Accurately projected meteorological conditions also can help to improve the results, and hourly or minute time series will lead to smaller error. Thank you for the attention.
You're spot on time, so we have time for questions.
So in the beginning, you were explaining about the complexity of the problem, and it's not only about rain. So how many of those features were landscape or geology based?
We have?
Yeah.
We have nothing. Actually, they are even not measured because some of the rivers are long with kilometers, and it's impossible to have sensors all over the river of the soil and different kinds of sensors because, as I said, there are temperature fluctuations in the vessel, so we cannot measure them. That's why we use machine learning, because that's the only way how the pattern can be learned.
This would be my second question. I wanted to ask you this. Temperature fluctuations.
I cannot explain at its finest because I'm not a meteorologist, but I can explain in general. For instance, if it is a place where the temperatures are high for years, it means that that soil will be so dry. Or if it's a place where there are 4 different seasons, then the soil will be different. What it is composed of.
So, like, with changing of climates, then basically, like, for example, these models would have to be rebuilt.
True that. That's why that is also one of the reasons why they need now new models, because they cannot predict on the historical data anymore. It's absolutely different from the last 10 years, for instance.
I have another question. About when we are comparing the different models, I have noticed that like only for the support vector machine, like if you use less features, the error is smaller.
Here?
Yeah. Do you have like an idea why is that? I mean, or is this just a property of SVMs? Because I'm not that well versed in using it.
No.
Can I jump in with a sub question of this one?
Yes.
Did you fit the parameters of SVM in any way?
I didn't. I used them as they are from.
So maybe this might be the reason, because SVM should be quite robust regarding the useless features. So this is quite a strange result, actually. But if you did not fit the parameters, of course, SVM is robust regarding the useless feature because it's very non-robust regarding parameter values. So you have to fit the parameters for it to operate properly. So maybe this is the reason for such a behavior.
Okay, thank you for the suggestion.
Okay, so here you have select K best.
Yes.
But this still uses another method.
No, this is the method I used. This is a class from SKUI. Like
Isn't that
already done. I just
yeah,
applied.
but you still okay. I thought that you still need to input some parameter based on
Yeah. The only parameter that you put is the number of features that you want to be selected as the
Does
best.
it work on like mutual information or this person?
Recursively. So it trains and recursively it chooses the best
Like
n
a web,
features.
like a web.
No, I think there is
Why
a
don't
metric that you specify by which it selects the best features, but you probably chose the default metric, which I think is mutual information.
I think there was another question there.
About the features, you said that some power plants have different features. Is that because they have different weather stations?
No, only for one hydropower plant we obtained different features, but it was a question of money. Actually, we took the data from Dark Sky, and after that, Dark Sky was bought from Facebook, and we should pay a huge amount of money to obtain the features for the last hydropower plants. Something like 1,000 euros for one hydropower plant. Because the period of 10 years is the period we were working on.
You mentioned the hourly and minute sample, right? Which one did you use here?
We use on daily basis, but if we have on minutely or hourly, probably the models will give better results.
Any other questions? If not, then just one comment maybe from my side regarding the weather data. You said that your data source shifted to commercial one, which gave you problems. There is a Copernicus system of the European Union, which is giving this kind of data for the last 50 years on their Copernicus portal. It's not the easiest to use, but you can access this data.
But for the past.
For the past 50 years on hourly basis for each location.
Yes, okay, but we need for the future. For instance, if we have the data, weather data for the next 1 week, then we can develop models for the next 1 week that would predict the inflow.
There might be also predictions there. I'm not sure. I'm sure for the past data, if they would have predictions, that would be perfect. So
yeah,
maybe it's worthwhile to check in the future work.
Yeah.
Okay, thank you very much again.
Hello everyone, my name is Gaspar, and today I'll talk about IMF quality assurance of mammograms using deep convolutional neural networks and transfer learning. Here is a brief outline of my presentation. So I'll start with the introduction to quality assurance in mammography. I'll talk a bit about the background, the relevance, and the usefulness of it. Then I'll go briefly through some of the state-of-the-art, what people are doing in this field. Then I'll go in more detail about the data that we used and some of the pre-processing that had to be done, both in terms of labels and the images themselves. Then I'll go into more detail about our computer vision methodology, where I'll talk about our networks and our experimental setup, and I'll conclude with a summary, some conclusions, and future work. So to start, what is mammography? It is the usage of low-energy X-rays for breast tissue examination. And it is the de facto standard for early detection of tissue anomalies, and this is especially related to breast cancer. This is a regular periodic screening for women, especially when they get older. So with age, the frequency increases. However, the procedure itself, as seen on the right here, is relatively complex and quite uncomfortable. So the patient has to adjust themselves into a suitable position on this large device. the technician has to set up some of the parameters, etc. So it is, like I said, quite uncomfortable. Also, the patient is obviously exposed to X-ray, which is not ideal. So the goal here is always to get high quality and useful images. So to get as little poor images as possible so we don't have to repeat the process. And these mammograms are typically recorded in two views. One is craniocaudal, or CC for short, and this is when the image is made from top to bottom. The other one is medial-lateral oblique, or MLO, and this is when the image is made from the side. And each of these views captures some of the same information, but some of it is also different. Here on the top right, you can see a CC view example. Ignore the text on it. Those are just some labels that I'll go into more detail later. But the idea here is that if we look at the bottom one, which is the MLO, and the top one, which is the CC, we can see some obvious differences. And the main one is that the bottom one, so from the side, we have the presence of the pectoral muscle, which is the sort of the whitish area on the top right side. Then once these images are made, each image is evaluated by an expert, and one of three labels is given, so the image is either poor, moderate, or good in terms of quality. And like I said, the idea is to minimize the amount of poor images in order to avoid any rescreenings and to get good images to the doctor. So currently, state-of-the-art main use case here is computer-aided diagnostic, specifically for breast cancer detection or risk prediction. As you can imagine, deep learning approaches dominate because it is a computer vision task, and classic computer vision architectures like convolutional networks and autoencoders are dominant. Here on the right, I've shown some examples of what people are detecting. For instance, there is some anomaly in the tissue that changes with time, or there is an appearance of some anomaly that is very small in the bottom case, but these are the type of things that they're trying to detect. There are challenges, obviously, here, as with most things, and these are especially in relation to deep learning approaches. One is obtaining enough data, which is labeled, and the thing is, generally, obtaining images is not that difficult. However, when medical images come into play, the things become more difficult because, for instance, in Slovenia for sure, but probably in Europe, I think the regulation is that the medical image that is taken in one institution, for instance, in our clinical center, cannot leave physically, the file cannot leave that institution, so it is difficult to get those files for actual training, for instance. Another problem for our use case, for instance, is that even the data that is available in terms of mammography does not have labels, typically, at least not in terms of quality assurance. Typically, there are some things like tissue anomalies or cancer are labeled. So the question for us was, can we classify mammograms of different quality automatically in order to get good images? So a bit more about our labels. As I mentioned previously, a person is grading these images, and there are actually a lot of grades, both for CC and MLO views, 9 for CC specifically and 10 for MLO. Some of them are the same, but some of them are different. Like I said, in MLO, we have the pectoral muscle present, so some of these grades are related to that one, and that's why they're different from CC. An important thing here is that some of these quality grades are quantifiable and measurable. For instance, again, the example here would be pectoral muscle, and quality grade metric here is the angle of the pectoral muscle. And this is something that you can measure precisely, and there is an if-else rule. If under, 20 degrees, one grade, else something else. But some of them are basically learned by the experts as they go, and they are expert subjective. For instance, an example of this is the IMF that I'll talk more about. The ultimate grade is given as the maximum of individual grades, which are numeric, but the idea here is that if an image has, for instance, 10 grades that are good and just one grade that is poor, the whole image is classified as poor. And for our use case here, we will just focus on one of these grades, and this is the inframammary fold, or IMF, which is present only in the MLO view. And here on the right side, we can see the region of interest that is basically, it's marked by the expert, and this is the area where they look for this, and the area that they use to give the grade. So more about this IMF. Here's some information that I've gathered from a paper, or it's not really a scientific paper, it's just an article. It's called The Elusive IMF, What, Why, When, and How. So what exactly is it? It's defined as the crease between the breast and abdominal tissue, as you've seen in the region of interest previously, and I will show it again. Now the why. It is an important anatomical landmark to provide assurance to the technologists and radiologists that all the breast tissue has been included. However, there is no published data regarding the definition of the visualization of IMF. So the question now becomes how much, how to put it exactly, and each radiologist may feel differently on this. So, for instance, the author of this article, who is also a radiologist, said that based on his opinion and experience, he gives some guidelines. And the answer to how, from our side, is obviously using a computer vision model, a deep learning model that will predict the quality grade for IMF automatically. Regarding to what I was talking about previously, here is an example. The left image here shows an improper case, which has a poor grade, and the right one is a good grade example. And these two rectangles, the red one and the green one, are the regions of interest that radiologists or the experts look at. And we can see that the difference, looking at the white arrow position, is actually very subtle and not obvious. If one were to look at just those rectangles, it's very difficult to say something about these two cases. So for our data, in terms of labels, we had a relatively skewed distribution, which is an inherent problem with this quality grading, because the vast majority of images are graded as good. So the poor cases are relatively rare. In our case, we had around 4,500 mammograms with corresponding grades, but 4 of each correspond to one subject, because we always have left and right breast tissue, and we have the two views, so CC and MLO. So since we only took MLO, that is relevant for IMF, only half of these were used in our experiments. Now, in the images themselves, there are some problems. One is that the view plus position type of stamp is given on each image. So in the top left or top right corner, it says either MLO or CC plus R or L, which stands for right or left. And this we wanted to remove because we didn't want the model to basically infer anything from these letters. Then, of course, these images are of different size. They're not consistent, which is a problem. And obviously, often they have poor contrast. So some of the things are quite difficult to see with naked eye. So what we did to resolve this was first to remove those stamps that I talked about, not to have the model learn anything about that. Then we improved the contrast using an adaptive histogram equalization technique. This is a relatively standard technique in basically in X-ray imaging, or basically analysis from X-ray images, because it increases the contrast and helps experts see things even with naked eye. Then we downscaled and resized the images to a consistent size and unified the direction so that all of them were facing the same way. Here is just an example of what this adaptive histogram equalization does. Here on the left side, we see an MLO and CC example, and on the right, we see the pre-processed versions, and we see that the contrast actually enhanced. So some of the things are, especially in the bottom left part of the image, are more easy to see. Now, in terms of our problem, we had a typical classification problem. So we had 3 classes. However, we mapped this into an ordinal regression because we had this typical grading problem. So the class labels 1, 2, 3 were actually mapped to a continuous interval between 0 and 1, where basically the left side of the interval was one grade and the right side was the other one. And for us, it also mattered how close we are to a prediction. So if we predict something with 0.01, it's different than if we predict it with 0.2. The pipeline itself was relatively classic, so we had these MLO view images as input, we had a chosen neural network architecture, and then we outputted the grade. Now, for our architectures, we investigated 2 deep learning architectures. One was a simple convolutional network. Here we had a couple of convolutional layers, some max pooling, and a couple of dense layers. We built this from scratch, and it's just something that we based off of related work and something that works well in image recognition in general. But then we also investigated a transfer learning approach, and here what we did was we took the VGG19 model, which is pre-trained on ImageNet, and we just retrained the final couple of layers for our data to see if we can get like a model that's pre-trained on a lot of images that already learns how to derive some features, and then just use this on our case. For the pipeline itself, we had, again, a relatively standard stratified 5-fold cross-validation. We monitored a couple of metrics, so root mean squared error, the area under the curve of ROC curve, here looking at pairs of grades, so grade 1 versus 3, 1 versus 2, and 2 versus 3, and then accuracy for some intuitive feeling of how well it works by mapping back from regression into classification, into discrete classes. And again, as I mentioned at the start, the most important thing is to recognize the poor examples. Here are some numeric results. The top part is for the simple model. The bottom part is for the VGG19 model, where we did transfer learning. Overall, the simple model, so the simple CNN, worked better across the board. In terms of accuracy, it achieved like 94%, but I have to say here that even the majority class is at around 64–65%. But perhaps the most interesting one is the area under the curve of 1v3 case, where we have a 0.95, which shows that we have a relatively good separation between the good cases and the poor cases. Then looking at the other two examples, so good versus moderate and moderate versus poor, here things become less good because this is inherently a more difficult problem because these images are more similar to one another compared to good versus poor. Now, this is all fine. We had a network which appears to work okay. It has decent results, but now the question becomes, what did the network actually learn? So, is it following the expert's region of interest, or is it following something else entirely? Is it something that the experts just don't know about? Is it something that's this data set specific? Well, what's happening here? So what we did here is we took basically some mechanism of visualization of what the network learned, and we used GradCan, which is basically, it uses the gradients to produce a heat map showing basically where the network was focusing. And if we go back to the image that I was showing earlier of that MLO view, we see the region of interest marked by the experts was in the bottom right. And here is an example of our prediction heat map. And we can see that the model actually focused the area that is also focused by the experts. And this is something that happens consistently across the data. Not always, but relatively consistently. So to summarize, we classified IMF grade from MLO mammograms. We achieved reasonable performance with a relatively simple model, and the model actually learned the relevant region of interest to look at. The transfer learning approach that we checked did not work as well. It did learn something, but not as well. And the use case we see in this is in mammogram quality assurance to give immediate feedback to the people who give grades and to have a sort of training loop where an expert can see a grade that the model gave and perhaps also some interpretation in terms of the heat map where the model was looking to at least maybe reconsider if the grade is different. For future work, of course, we would have to look at other grades as well. This is IMF is just one of them. We could fine-tune the model. This is relatively simple, and we could do region of interest segmentation at first to just find the part that's relevant and then do the grading, etc. Now, just for the team, I'm actually the only one from JSI. I had a couple of colleagues from the industry working with me, and then also a couple of colleagues from the Faculty of Health Sciences. And that's it. Thank you.
Very much. Any questions? Everybody's amazed. So you learned that using this convolutional neural network, which was learned from scratch, is better than the transfer learning one. Do you have any explanation why? Did you check what kind of features they learned, you learned?
Yeah, I didn't check the features, but I have some intuition of why this might happen, and that's because training on ImageNet, which is the database that was used for pre-training of VGG, those images are actually quite different compared to X-rays. So probably the features that were learned there are not as useful for the X-ray case that we did here. So probably an option would be to fully retrain VGG architecture from start to finish with our inputs, and then it would probably learn features for mammograms. However, the network is large. It's 19 layers deep and relatively large, so the training takes time. So we didn't do it yet at this point.
Could you present these focus areas also for the VGG?
Yeah.
Or it is not possible?
Yeah, I think VGG is a CNN architecture, so convolutional, and I think that GradCam basically can be applied to any CNN-based architecture. So I think we could use GradCam to look at what VGG was looking at as well.
Thanks. Now we have, I think the first question was there, yeah.
I have one quite practically oriented question. How hard is it to actually work with like medical data that's protected and everything? Like compared to other projects, would you say this was like, I don't know, 2 times or 3 times more work to just like get the data, get all the papers done?
Yeah. From my side, this was relatively comfortable because when people came to me, they said, "We have the data. Can you do something with it?" So that was fine from my side. But if you're at the starting point and you don't have the data, it's quite difficult. They are very reluctant to give data out. It's very difficult to approach these people in general in oncology. They're very protective of data, so it's quite hard to get it. I think that, coming to a point where you have a data set that is useful probably takes some time, but luckily I was spared this part.
Yes, the images look to be, as far as I understand, this is the X-rays are basically black and white, right?
Yeah.
Could it be like related that VGG is by default pre-trained on probably full color images?
Yeah, it is. That was part of the thing that I was explaining. Yeah, I think VGG is pre-trained on color images, which are quite varied in general and also different inherently by being color images, not.
I mean, applying deep learning on radiology images is a pretty common thing to do. Are there any large and nice pre-trained networks for this kind of images? I mean, I would expect there to be some.
Yeah, I mean, I think you're right in terms of that this is a common thing and people are doing it all the time. As far as availability of pre-trained networks go, in general, from my experience, it's hard to get pre-trained networks for like, let's say, smaller papers or something like that. It's much easier to get it something from Facebook or Google or whatever. But maybe it is possible. We didn't go into that much detail, but might be worth investigating or contacting some of the authors that did this, get a network.
Questions? Thank you very much. The next is online.
Hello.
Hello.
Can you hear me?
Just maybe a few seconds that we prepare also the slides.
Okay.
I think that she needs to share the slides. Are you now sharing the screen?
You have to give me a permission to share my screen. So now I don't have permission to share my screen. So. Just a second. I'm sorry.
So we currently do not see anything yet.
Let's check. Okay. I don't know what's the problem why I cannot share my screen. Okay. So can you see my screen now?
Yes, yes, now we can. Cool. So just before we start, there is a good news and a bad news. The bad news is that I will have no control over you because I'm sitting over there. The good news is that we have some spare minutes anyhow, so just relax and give your talk. Thank you.
Thank you. So, hello everyone. My name is Maria Chushevska, and today I'm going to present our work with the title Learning the Probabilities in Probabilistic Context-Free Grammar for Arithmetical Expressions by from Equation Corpora. Before we start, let's look at the outline of the presentation. So first, we are going to talk about the equation discovery task. Also, next we are going to talk about the grammars for equation discovery. More precisely, we are going to talk about context-free grammar and probabilistic context-free grammars. Also, we'll define the parameter learning approach that we actually have used for the purposes of our work. Next, I'm going to explain the corpora of equation that we have used in this work and see the results and discuss them. And at the end, we are going to conclude our work and discuss our ideas for further work. Equation discovery is actually an area of machine learning that develops methods for automated discovery of quantities laws in the forms of equations. This task is actually closely related to the task of supervised regressions. There are many equation discovery systems that have been developed through the years. One of them is actually Lagrange, that uses context-free grammar to specify a language of the equations considered. And one of the most recent equation discovery system that uses probabilistic context-free grammar is ProGet, which stands for Probabilistic Grammar-Based Equation Discovery. And for the purposes of our work, we are using this equation discovery system. Equation discovery systems actually explore the hypothesis space of all the equations that can be constructed given a set of arithmetical operators, functions, variables, and they actually search for the equations that fit the input data best. And the number of all the possible candidate equations can be infinite. When we talk about equation discovery, the most important part of equation discovery are actually grammars. A grammar is a final specification of a language, where a language can contain an infinite number of strings, and they are used as a formal specification of languages that contain a set of production rules. And these production rules are used to derive strings, or in our case, we have a set of equations. So also all the grammars for equation discovery distinguish between non-terminal and terminal symbols, and one specific non-terminal symbol, which is start symbol. We are going to actually talk more in detail about these symbols, non-terminal and terminal, in the next slides. So one of the grammar that is used for, one type of grammar that is used for equation discovery is actually a context-free grammar. It's a formal specification of a language that is used to generate all the possible patterns of strings in a given formal language. And also context-free grammar is also defined as a generator of legal strings from a language. That's why equation discovery is usually defined as a language of mathematics. Context-free grammars are defined as a tuple of non-terminal, terminal symbols, set of production rules, and a start symbol. Terminal symbols are non-terminal symbols are actually represent higher order terms in the language, such as noun phrase or verb phrase, where on the other hand, terminal symbols are usually elementary symbols of the language expressed by the grammar. They are usually words, or in our case, variables, because we have a set of arithmetical expressions. S is a start symbol, and R is a set of production rules, where the left-hand side is a non-terminal, while on the right-hand side is actually a string of non-terminal and terminal symbols. And actually, the syntax of the expression on the right-hand side of the equation is prescribed with a context-free grammar. The other grammar for equation that is used for equation discovery task is actually a probabilistic context-free grammar. This grammar is an extension of context-free grammar, because we assign a probability. We assign a probability to each production rule. So probabilistic context-free grammar has 5 parameters: a set of non-terminal symbols, terminal symbols, start symbol, a set of production rule, and the 5th parameter is actually the probability that is assigned to each the production rule. And actually, these probabilities that are assigned to the production rules provide a great amount of control over the probability distribution of individual parse tree. And the probabilities of all the production rules with the same non-terminal symbol on the left-hand side has to sum up to 1. And also, when we derive a given string or expression using a probabilistic context-free grammar, the parse tree that we get at the end, so the probability of the parse tree is actually production of all the probabilities of the production rules for that parse tree. The corpora of expressions, arithmetical expressions that we have are, so we have 2 corpora of expression. The first one is Feynman symbolic regression database that actually has 100 equations from the 3-volume set of physics textbook. And this database has been used as a benchmark for equation discovery. All the equations in Feynman database consist of variables, the basic operators, plus, minus, division, multiplication, functions like exponential, sqrt, sine, cosine, tan, hyperbolic function, ln, arcsine, constants, rational and irrational like E and P. The other corpus that we have and that we used for the purposes of our work is a Wikipedia corpus that consists of 4,080 mathematical expressions. And also here equations consist of a lot of variables, the basic operators, functions, and there here these underlined functions like absolute value, factorial, tan, sin, sine hyperbolic function, cosine hyperbolic, and pau actually are not present in the Feynman regression, symbolic regression data, and also constants, rational and irrational constants. Here are some basic statistics of the 2 corpora of equations that we have. The minimum number of constants per equation is 0 in both databases. The maximum number of constants per equation in the Feynman is 5, where in the Wikipedia is 16. So we can notice from this table that actually Wikipedia dataset has higher number of constants per equations and variables per equation, and also higher number of functions that are used and that equations consist. Here is actually how the universal probabilistic context-free grammar with some initial probabilities from ProGet looks like. So these are actually the production rules, and we can notice that there is a probability assigned to each of the production rule. And the sum, so the probabilities of all the production rule with the same non-terminal symbol on the left-hand side of the equation has to sum up to 1. So if we sum the probabilities of this production rule, so they sum up to 1. Okay, so we use actually, so this is the universal probabilistic context-free grammar from ProGet, from the most recent equation discovery system that we used in this work. So the primary learning approach here is actually based on parsing an equation corpora of expressions. So we are using a universal probabilistic context-free grammar with manually assigned probabilities. So the one that I mentioned in the previous slide, and a parser from Natural Language Toolkit Python library. So we used actually inside chart parser that it's a bottom-up parser that tries edges in the descending order of the inside probabilities in their trees. So we actually assume a fixed set of probabilities that are manually assigned, and for a given string, the parser actually determines whether the string, or in our case an equation, can be derived using that grammar. And if yes, then it returns the appropriate parse tree. At the end, how we update the probabilities, how we learn in the way that we count the number of times each production rule appears in a set of parse tree, and then we group the probabilities by the left non-terminal symbol and derive the probabilities for each production rule as the number of appearances of a given production rule divided by the sum of such number of all the production rules with the same non-terminal. And after this parameter learning approach, we get two new grammars with, so the first one is actually the grammar with probabilities learned on a Feynman database, and the other one is a grammar with probabilities learned on the Wikipedia's corpus. Here's an example actually of one parsed equation from Wikipedia. So these are actually the variables, and C is a constant. So this is a parsed equation using the universal probabilistic context-free grammar with manually assigned probabilities and the inside chart parser. So this is the probability here is actually a production of all the production of all the probabilities of the production rules that are used to derive this this equation. So now let's look at the probability distributions and discuss the results that we got. So here is actually a graphical representation of probability distributions for the S non-terminal symbol for all three grammars. So the first grammar is actually the probabilistic grammar, context-free grammar with initial probabilities. This is with light blue, light green color. Then the probabilistic context-free grammar with probabilities learned on Feynman dataset. This is with the dark green color. And the probabilistic context-free grammar with probabilities learned on Wikipedia corpus with orange color. So from this graphical representation, actually, we can notice that Feynman database actually reduces the probability of the recursive production rule S plus F and S minus F, but increases the probability of the non-recursive production rules, which actually this indicates that actually Feynman database leads to create simpler expressions with fewer additive terms. On the other hand, the probability, here is the probability distribution of the non-terminal F non-terminal symbol. So we can notice here that both grammars, so Feynman and Wikipedia, actually tends to increase the probability distribution of the terminal of the production rule F multiplied by T. in compared to the initial grammar. On the other hand, the non-recursive production rule F goes to T, so they reduces both grammar actually reduces this probability compared to the initial grammar. The probabilities on this slide are shown the graphical representation of the probability distribution of the T non-terminal symbols. And here, the most drastic and notable difference that we can notice is that actually initial grammar underestimate the number of constants in both grammars. So underestimates actually the number of underestimates the number of variables in both grammars. But on the other hand, the probability of the constants here actually are reduced in both the grammars compared to the initial one. And here on the last graph are actually shown the probability distributions of the production rules for the functions. The zero values actually indicates the zero values of the probabilities indicates that those functions are not they are not present in that corpus. For example, I don't know, arcsine actually is not present in the Wikipedia corpus, so that's why the probability is 0. Or sine hyperbolic function, cosine hyperbolic function, factorial, these functions are actually not present in the initial grammar and in the Feynman dataset, so that's why their probabilities are assigned to 1. What we can notice from this graphical representation is that both grammars, Feynman and Wikipedia, actually increase the probability distributions of the terminal of the production rule R goes to S compared to the initial grammar, and decreases. So Wikipedia corpus, Wikipedia dataset actually decreases the probability distribution of the production rule R goes to S. So to sum up, we can say actually in this work we have proposed an approach to learn the parameters, or the parameters are actually production rule probabilities in probabilistic context for grammar using by parsing equation corpora and using natural language toolkit Python library, so a parser from natural language toolkit Python library. And we can say that that learned probabilities actually differ from their initial values, from the manually assigned probabilities. And the most notable difference is that the initial settings underestimate the frequency of variables in favor of numerical constants. And also the results show that it's very difficult actually to set the probabilities manually and highlight the utility of the learning algorithm. And as a further work, we have a plan to make an equation discovery experiment using these 3 probabilistic context-free grammars. So the first one is the initial, with the initial probabilities. Second one is the probabilistic context-free grammar with probabilities learned on Feynman database, and the third one is probabilistic context-free grammar with probabilities learned on Wikipedia corpus and ProGet, the most recent equation discovery system. So this equation discovery experiments actually include generating a bunch of candidate equations using these grammars, estimating their parameters, and at the end to see how many equations are going to be successfully reconstructed with these 3 grammars. also using by ProGet. So thank you very much. Thank you for the attention. If you have any questions, feel free to ask.
Yep. I will first ask the audience which is here live, and I'll try to repeat the question if you will not hear it. If we have any questions, do we have any? No, so it was all clear, I think, for this audience here. And I would invite now the audience online to ask if you have any questions for Maria. No, but I have one. It's a short and simple one. So this manual assignments of probabilities from ProGet, they are not totally off in most cases. So how are they made? So is this done by experts manually, or how is this designed?
No, actually, they are randomly assigned probabilities. Randomly assigned probabilities. So you can manually change them.
So that was a random assignment. So the process that you're showing could work even if this would be assigned, let's say, that each option would have the same probability, so that you would have a uniform distribution. It should work as well.
I'm sorry, I didn't hear the question.
So if you would start with a uniform distribution, would it work as well?
If we start with uniform distribution?
Yeah.
But we can start with uniform distribution, but the learned probabilities that we get now by learning the probabilities is actually uniform distribution. So we will probably get the same results as now.
Mm-hmm. Okay. Thanks. Then I will have to ask a few more questions, but I'm afraid there's not enough time right now because we have a break and we're half a minute late. So thank you very much, Maria.
Thank you.
And now we go for a break.
Adriana, you're welcome.
The title of my presentation is on our initial results in predicting high-level features of constrained multi-objective optimization problems. The outline of this presentation is as follows. We will give an introduction, overview, we will present the methodology, the results, and finally I will give a conclusion of our work. So I will start with the problem formulation. So what are constrained multi-objective optimization problems? In optimization problems, usually we want to find the minimal or the maximum value of some function. And then, if we have two or more functions, then we are dealing with multi-objective optimization problems. However, these functions are usually not they are in conflict with each other, and because of this, we cannot find a single solution that solves the whole problem. But we get a Pareto front of solutions that represent some compromise between the objectives that we try to solve. And also, because we have constrained multi-objective optimization problems, we have each solution can be either feasible or unfeasible. And the collection of all feasible solutions can be represented as the feasible region of the space. Now to the motivation. So let's say that we have some constrained multi-objective optimization problem that we are trying to solve for the first time. And what we try to do, we try to have different algorithm and constraint handling techniques that we can use. But if we apply all possible combinations of algorithm and constraint handling techniques, we will lose a lot of time, and this is also sometimes not feasible to do. So what is more reasonable is to use some high-level features that
help with the algorithm and the constraint handling technique choices. These high-level features represent, let's say, how what type of problem our problem belongs to, and then we know that for this type of problems, some algorithms are good and so on. However, these high-level features are hard to calculate, and they're time-consuming to calculate. And because of this, in our work, we try to use low-level features that are cheap to calculate to predict the high-level features. The low-level features are calculated as following. So they're a large, each problem has a large number of solutions that we can find, but it is, we cannot evaluate all the solutions. So what we do in real life is that we select a sample, let's say 500 solutions. We evaluate these solutions, and then we try to extract some statistics on how these solutions interact between each other. And these statistics can be defined in 5 different categories in our case. Global features, multimodality features, availability, ruggedness, and constraint features. And this is it. So in our methodology, we try to use 14 benchmark problems that were proposed by Ma and others in 2019. Now, when they proposed this benchmark, they said that the most important high-level features for this benchmark is the problem type and the problem connectivity high-level features. And in our case, we used only 5-dimensional benchmark problems, and also to calculate the low-level features, we used 2 to the power of 9 number of solutions. Now, here I present the high-level features that we will try to predict more thoroughly. So one is the problem type, and the other is the problem connectivity. The problem type represents the relation between the Pareto front in if we don't apply any constraints on the problem. This is the black line on this on the left part of the image. And the red line represents the Pareto front after the constraints have been applied. And you can see, let's say for the problem that is on the left side, the most upper, on the upper left corner. In this problem, the Pareto front for the constraint and the unconstrained problem is the same. And here we don't need to apply any constraint handling technique. Any multi-objective optimization algorithm will find this Pareto front, the approximation of this Pareto front. For the problem connectivity, this is actually the connectivity of the feasible region. And as I said, all possible feasible solutions represent the feasible region. And the feasible region can be either not separated, or it can be separated into different subfields of feasible regions. The overview of our methodology is as following. So first, we have these optimization problems that we used. This is the MW problems. And then for each problem, we calculate 100 different samples of solutions. And this means, and for each sample, we calculated the low-level features. Now, this means that for each problem, we get 100 instances of low-level features. And because we have 14 different problems, we have 1,100 instances in our data set. Now, we use these instances to train machine learning models, which we will try to predict the high-level features. To evaluate our methods, we use three different types of evaluation methodologies: the train test split, the leave one problem out, and gradually adding instances from the target problem into the training data. In the train test split, we use 50% of the instances for each problem as into the training and 50% into the testing set. In the leave one problem out methodology, we use the instances from one problem for testing and the instances from all other problems for training. And in the last evaluation methodology, we gradually add instances from the target problem into the training data. Now, with the train test split, we get quite high classification accuracy, around 100%. However, when we use the leave one problem out evaluation methodology, we get much lower classification accuracy. And this was strange for us. So we applied an additional experiment. This is the third evaluation methodology, in which we gradually added instances from the target problem into the training data. And here we saw that with adding only a single instance from the target problem into the training data, we get much higher, actually around 90% classification accuracy. To explain why this happens, we can see these visualizations. Now, in these visualizations, we have what we did was we got the feature space and we reduced it to 2 dimensions. Then each instance is plotted based on this two-dimensional reduced space. Now the colors represent different information that we want to represent in these figures. In the leftmost figure, we have the color represent to which problem the instance belongs to. And here we can see that, for example, the yellow one, I'm not sure if you can see it, but there is a circle here that is colored with yellow color. And in this, we can see that all instances form some kind of clusters, and these clusters are colored with the same color, which means that the instances form some kind of clusters, and the instances from the same problem are close to each other, and because of this they form clusters. However, if we see the problem connectivity and the problem type, the colors in there, we cannot see anymore these clusters or some kind of rules in the data, especially in the problem type, the colors are scattered all around the place. In this, the middle and the rightmost figure, the colors represent the class that represents the problem, and the instances that have the black border are actually the instances that are classified correctly in our case. So here we can see that actually with random forest, random forest works a bit differently. So maybe it's better to see the visualizations from k-nearest neighbors. And here we can see, because this is a method that finds the closest samples. And here we can see that all instances that are here plotted close to each other and have the same color are colored with the same are correctly classified. And in the case of predicting the problem type, we can see that only this part, so there is only one problem that is correctly classified, and all the other problems, the instances are not classified correctly. To conclude this presentation, then I will say this. In further tests, we found that applying the train test split is not sufficient. So we should, because in the real world we will get a new problem for which we don't have any information, and this is why we should use the leave one problem out methodology. However, this is a much harder method. The results are not so well in this methodology, and a possible explanation for this is that the low-level features are not do not represent the high-level features well enough. They don't have any information about this. Finally, we also saw that the visualizations showed that instances of a single problem are really similar to each other, and they form clusters. So because of this, we saw this, and because of this, the train test split showed much higher classification accuracy, while in the leave one problem out, we get much lower classification accuracy. So thank you for your attention. If you have any questions, you can ask now, or these are our contacts.
Presentation. I invite comments or questions. Go ahead.
Yes, on slide 7. Could you please explain once again this image on the left?
The image on the left, this one. So here with red, I'm not sure how well you see it. Okay, so with the black line, it's the unconstrained problem, while with the Pareto problem, it's the unconstrained problem, and with the red line, it's the Pareto constrained problem. And why is this important? It's because when algorithms try to find solutions, this also is quite important, because if we know this characteristic, we know which constraint handling technique to use or algorithm to use. So this is an important high-level feature.
What are the 4 images?
Because in the first image, the Pareto front of the constraint and the unconstrained problem have all the solutions in common. In the second problems, the solutions in the Pareto front from the constraint problems are all in the belong all in the Pareto front of the unconstrained problem, but there are also solutions from the unconstrained that are not. And here, there are also some solutions in the unconstrained that don't belong to the constrained problem. In this case, none of the solutions, the solutions from the Pareto front are in common between the constraints.
So those are basically all possible variations.
Yes, these are the feature. This is the high-level feature, and if we know this, then it's quite informative to know which algorithm to use. This is the idea.
So obviously it could be what you said, that low-level features are not informative about high-level features, and in that case you're kind of doomed. But could it also be that you simply don't have enough data? Because I mean, your number of instances is decent, but the number of problems is pretty low. So is it possible to get a lot of new problems? Is it easy to get? Is it hard to get?
Yes. So this is also one of the future works that we will try to do, because we used only one benchmark so far, but we can also use other benchmark problems to in our data. So we will for sure try this as well. For sure, using more problems is also. However, it's not so easy to find constraint multi-objective optimization problems for which we know the high-level features.
But when you say that high-level features are hard to get, what does it mean? I mean, does it mean that in some cases you just can't do it, or that it takes a lot of computation? Or
it takes a lot of computation. We need to evaluate a lot of solutions in the search space to know these properties. Because it might happen in this case, if we have some samples, then it might happen that there is actually some connection, let's say up, that these two regions are connected, but we have to be really precise in the search space.
We have time for one more question. David, go ahead.
You mentioned that train test split was not okay, but leave one problem was okay. Isn't this the same thing? It's like a k-fold with different k.
No, the idea is here. So what I tried to, I started saying, but then I think I jumped ahead, was if you see here, let's say that here we select the MW9 problem, which is yellow, and it's the yellow circle there. So you can imagine if you leave some instances from this problem, 50% of these instances, then you can still capture where these instances are located, right? But if you don't use any of the instances there, if you eliminate that problem, then the neighboring solutions are quite they're colored differently in the next two slides, and this is how we explain this. So this is why it's much harder problem.
Okay, thank you for your questions. Again, if anyone has a question, Adam, take it.
Thank you.
Juliana, I just wanted to add that, again, if anyone has questions online, they can also speak up, even if I don't prompt them. But if there are none for this presentation, I'd say you're welcome to present yours.
Pozdravljeni, jaz vam bom pa predstavil naš članek z naslovom Študija učinkovitosti algoritma za razporejanje terenskega dela. Torej, problem razporejanja terenskega dela je problem, kjer želimo vsaki nalogi dodeliti delavca ter čas izvedbe. Rešujemo ga s trinivojskim algoritmom, kjer najprej naloge razdelimo po delavcih, nato jih razdelimo po dnevih, in na koncu še za vsako kombinacijo delavca in dneva vsaki nalogi določimo uro z algoritmom razvaj in omej. Ta naš algoritem lahko rešuje probleme z več 100 nalogami, saj na tretjem nivoju, ki je najbolj kombinatorično zahteven, vedno dobimo dovolj majhne probleme, ampak vseeno je ta tretji nivo precej počasen in zato ga želimo pohitriti, saj za velike probleme rabimo recimo 1 uro ali več časa. Najprej bom na kratko opisal optimizacijski problem. Torej, za vsako nalogo nas zanima, ali se izvede in če se, kateri delavec jo izvede in v kakšnem času. Pri tem mora biti zadoščeno vsem omejitvam, hkrati pa si želimo, da je cena razporeda čim nižja. Torej, omejitve problema so naslednje. Nobeni dve nalogi, ki jo izvede isti delavec, se ne smeta izvajati hkrati. Delavci lahko izvajajo naloge znotraj delovnega časa, lahko pa izvedejo tudi določeno število nadur. Vsak delavec lahko upravlja samo naloge, za katere ima kompetence. Vsaka naloga mora biti razporejena znotraj njenega časovnega okna in vsaka naloga z obveznim razporedom mora biti razporejena na čas obveznega razporeda. Želimo si, da je rešitev čim bolj ustreza vzdrženi vsoti naslednjih kriterijev. to so. Želimo, da so delavci obremenjeni čim bolj enakomerno. Želimo, da je število aktivnih delavcev čim manjše in da so ti aktivni delavci čim bolj enakomerno obremenjeni. Želimo si, da je trajanje potovanj med nalogami čim krajše, da razporedimo čim več nalog in da z upravljanjem nalog zaključimo čim prej znotraj dneva. Želimo si tudi minimizirati neaktivni čas, to je čas, ko delavci ne upravljajo nalog. Prav tako želimo minimizirati število nadur. Želimo si tudi, da so naloge razporejene po prioriteti, se pravi, da so naloge z višjo prioriteto razporejene prej kot naloge z nižjo prioriteto, ter podobno, da so razporejene po času zapadlosti, se pravi, da naloge, ki zapadejo prej, da se začnejo izvajati prej. Prav tako želimo upoštevati želeno časovno okno nalog, želenega delavca ter želene razporede. Zdaj bom pa na kratko opisal še algoritem, s katerim smo reševali problem. Se pravi, kot sem že rekel, je trinivojski in na prvem nivoju uporabljamo evolucijski algoritem, kjer določimo, kateri delavec upravlja katere naloge. Začetno populacijo ustvarimo naključno, vendar tako, da so rešitve dopustne. Potem starše izbiramo s turnirsko selekcijo, križanje pa upravimo naključno. Mutacij smo implementirali več, kjer vsaka sledi različnim strategijam in vsaka strategija nekako sovpada z enim izmed kriterijev. Potem vsako generacijo, staro populacijo prepišemo, ohranimo pa najboljšo rešitev. Se pravi, na drugem nivoju razporejamo naloge delavca po dnevih. To delamo s heuristično funkcijo, kjer izbiramo naloge od tiste, ki ima najmanj možnih dni izvedbe, proti tistim, ki imajo več možnih dni. In za vsako nalogo določimo najugodnejši dan z glasovanjem. Glasuje pa vsak izmed kriterijev in vsak izmed kriterijev glasuje z takim številom glasov, kot je njegova utež. No, potem pa na tretjem nivoju pa razporejamo, se pravi, samo še naloge znotraj dneva. In ta problem zapišemo v obliki mešanega celoštevilskega linearnega programa, rešujemo pa ga z uporabo knjižnic OR Tools in SCIP. Se pravi, za zapis problema z nalogami v mešani celoštevilski linearni program potrebujemo 3n kvadrat plus O(n) spremenljivk ter 5n kvadrat plus O(n) omejitev. In zato, da testiramo ta tretji nivo, smo ustvarjali 180 testnih primerov, po 20 za vsako število nalog med 2 in 10. In tukaj na grafu vidimo, kakšen je povprečen čas do optimalne rešitve. In vidimo, da za primere, kjer je do 5 nalog, se pravi, to deluje zelo hitro, za probleme z večjim številom nalog pa časovna zahtevnost narašča eksponentno. In ker je to seveda čisto predolgo za naš algoritem, smo temu tretjemu nivoju dodali različne časovne omejitve. In tukaj na grafu vidimo, kako se obnašajo, koliko je povprečno število razporejenih nalog pri različnih časovnih omejitvah. Zdaj, povprečno število razporejenih nalog ni najboljše merilo, ampak za to, koliko dobro deluje. Ampak vseeno vidimo, da pri večjih problemih to število razporejenih nalog zelo hitro pade. In to je pa zato, ker je pač kombinatorična zahtevnost toliko prevelika, da bi algoritem to lahko rešil v danem času. In zato se odločimo, da problem poenostavimo. In to naredimo tako, da na tretjem nivoju stranimo kriterija za urejenost nalog po prioriteti in po času zapadlosti. S tem se nam število spremenljivk in omejitev precej zmanjša. hkrati pa ta dva kriterija še vedno upoštevamo na drugih dveh nivojih in s tem jih še vedno nekako upoštevamo. Zdaj pa vidimo že s črtkanimi črtami, da recimo že pri časovni omejitvi 2 sekund algoritem deluje blizu optimalnega. Se pravi, smo s tem kar zadovoljni. Potem pa smo testirali še, kako ta poenostavitev vpliva na delovanje celega algoritma. Zdaj tukaj so grafi za 2 testna primera in za 2 različna scenarija uteži, se pravi, enkrat smo bolj utežili trajanje potovanja, drugič pa bolj enakomerna obremenitev delavcev. In vidimo na grafih, primerjamo, kako deluje osnovni oziroma poenostavljen problem pa pri 2 različnih časovnih omejitvah 1 in 2 sekunde. In vidimo, da v nekaterih primerih ta poenostavitev zelo pomaga, recimo na zgornjih 2 primerih. Na spodnjih 2 pa recimo niti ne, ampak vseeno pa algoritem zaključi v krajšem času. Hkrati pa vidimo, da tudi časovna omejitev 2 sekund pomaga in algoritem deluje boljše. To se pa sploh jasno vidi na spodnjih 2 primerih. Torej, v tem članku smo analizirali učinkovitost algoritma za razporejanje terenskega dela. Ugotovili smo, da je časovno najzahtevnejši 3. nivo algoritma in zato smo na tem nivoju problem poenostavili. Zdaj, pri poenostavljenem problemu algoritem že z omejitvijo 2 sekund deluje dovolj dobro in to hkrati tudi izboljša delovanje celotnega algoritma.
Hvala, malce, ker izvolite vprašanja ali pa komentarje, če imate.
Kakšnem problemu ste pa testirali te eksperimente?
Kjer eksperimente? To?
Ja, verjetno ste imeli nek scenarij.
Ja, recimo dobili smo od naročnika, smo dobili neke testne probleme, ki so jih zanimali. Potem smo recimo iz 20 problemov, ki smo jih dobili, smo potem nekaj izbrali na njih delali. Recimo pri teh, kjer smo pa mogli sestaviti za 3. nivo, smo pa sami sestavili glede na to, da so podobni takim realnim, kot so nam oni dali.
Ste pa so tudi oni podali, da razgledijo teži kriterijev in ste sami.
Ja, to smo nekako skupaj konvergirali k pravi rešitvi, ker je zelo težko, ker tudi niso enake enote in jih ni enostavno. Ampak ja, skupaj smo.
Obvezni razpored naloge?
To pomeni, da recimo, da ima neka firma že nekaj, kjer hoče, da je tam in da tega noče, da to ni predmet optimizacije, ampak je kot ovira, da druge naloge ne morejo biti tam. Ne smeš spreminjati, ampak je pa kot druge stvari ne smejo biti takrat.
Imam tu še kakšno vprašanje?
Nisem tako poglobljeno dojel, kaj se dogaja, ampak zdi se mi, da zato, da človek ugotovi, kako na višjih nivojih optimalno razporediti stvari, da bi lahko potreboval tudi informacije z nižjih nivojev. Je to tako ali ni tako? Ste se temu uspeli izogniti?
Seveda, ja. Se pravi, ko delamo evolucijo na prvem nivoju, potem evaluiramo osebke tako, da jih damo čez 2. in 3. nivo, da dobimo njihov fitness, recimo, in potem je to feedback za gor in potem na temo delamo.
Aha, se pravi, tako to deluje. Okay. Ja. Jaz sem najprej pomislil, da se pač najprej na enem nivoju, pa pol na drugem, pa pol na tretjem, ampak ne, v bistvu se znezdeno tako dela. Okay. Ja.
Še kakšno vprašanje? Mene še nekaj zanima, tam, ko si govoril o tem, kako se število kriterijev in omejitev skalira. Zdaj, a sem prav razumel, da je tam število nalog?
To je število nalog znotraj dneva, ki jih je treba razporediti.
In ta zmanjševanje te kompleksnosti, ki si jo omenil, kako to, da se toliko zmanjša kompleksnost, če en kriterij završi?
Ja, te dva kriterija sta, za njih je potrebno imeti vrstni red nalog, ne? Za vse ostale ni in moramo imeti za to permutacijsko matriko in to potem za zapis tega v mešan celokrivulski linearni program rabimo pač toliko več spremenljiv. In zato smo tudi te dva odstranili, ker sta bila najbolj potratna v tem smislu.
Pa bo še kakšno vprašanje ali pa komentar? Če ne, pa hvala še enkrat. Vabim kar Katjo.
Okay, hello everyone, my name is Katya and today I'll be presenting the paper with the title Unified Question Answering in SKUI. So question answering is one of the most challenging tasks in language understanding. Most approaches are developed for English, while less resourced languages such as Slovene are much less researched. This may leave some language specifics inadequately addressed because they are not present in English. For example, Slovene language is quite morphologically rich. We have noun and adjective declension, we have 3 counts, 3 genders, and also the person can be hidden inside the verb. Also, an additional problem that less researched languages have is a lack of suitable datasets for SKUI. In our work, we adapted a successful English question answering approach that is called Unified SKUI. The main idea of this approach is that we do not need to build separate models for different SKUI formats or SKUI datasets, because all those formats require a similar inference capability. That's why we can use a unified learning approach to learn all these SKUI formats simultaneously. The authors of this approach defined 4 different SKUI formats: extractive, abstractive, multiple choice, and yes/no format. The extractive format requires that the answer to the question is stated directly in the given context as a substring. Abstractive format requires some paraphrasing of the context, and also it may require linking information from different sentences. In the case of multiple choice questions, there are also possible options given, and the task is to choose the correct one. And finally, in case of yes/no questions, there are only yes or no as an answer. In our work, we focus mostly on reading comprehension. That's why all the dataset that we chose had the context next to the question. They were partially machine translated and partially human translated, but still the majority of the examples were machine translated. We considered 5 datasets, which is less than in the English approach where they used 8. 4 of them were already previously translated into Slovene. 3 were from the SuperView benchmark, and those were multi-RC, COPA, and BulkQ dataset. We also used the previously translated SQuad 2.0 dataset. And because we wanted to have an additional multiple choice dataset so that we could cover all the SKUI formats that I described previously, we also translated an additional multiple choice dataset that was the MC-test dataset. This dataset was translated partially with the commercial solution DeepL and partially with an internal neural translator. And we did this partial translation in order to reduce the cost of translation. We used different evaluation metrics for different data sets. For multiple choice and yes/no data sets, we use classification accuracy. For the SQUAD 2.0 data set, we use the F1 score. And for the abstracted data set, we use the Rouge-L metric. So let me tell you something more about the model that we use. In the original work, they use the T5 model. This is an encoder-decoder transformer, and it is based on the idea that all text-based language problems can be treated as text-to-text mapping problems. That means that both input and outputs of the model are textual. In that way, the same model, loss function, and hyperparameters can be used for different tasks, for example, for summarization, classification, or question answering. This model was trained on unlabeled data from the C4 corpus, and the training objective was the span corruption task. You can see an example in the picture above. In this task, they masked some tokens, and then the training objective was to predict those masked tokens. They masked about 15% of those tokens, and their average length was 3 tokens. Because this model is an English one, we used two different variants that were suitable for Slovene. The first one was the SLOT-T5 model, which is a monolingual Slovene variant. It was trained on a large Slovene corpora, which included various newspapers, books, and internet slang. And the second model that we used in cross-lingual transfer experiments was the MT5 model. This is a multilingual variant which was trained on 101 languages, including Slovene. In both cases, we used the smallest available models due to computational time and GPU memory limitations. So first, we obtained the so-called specialized models, which were trained on each QA format separately. Those models served as a baseline of what we're capable of achieving with a single QA format. Then we trained the model that we call SLO Unified QA, which was trained on all available datasets. And we discovered that this model, SLO Unified QA, outperformed specialized models on multiple choice and abstracted datasets. The improvement was minimal for extracted datasets, and the performance dropped slightly for the yes/no datasets. We also discovered that the model outperformed all main classifiers. The model also outperformed previously published results on the datasets Vulko and COPA, but not on SQUAD 2.0. However, in the first case, the authors used the same model, the SLOT-T5 model, where the output of the model is textual. However, in the second case, the slow beta model was used, where they only predicted the span of the answer, which is an easier task. Comparing the Slovenian results to the English ones, we discovered that the Slovenian results were worse for all formats, except for the SQUAD 2.0 dataset. In this case, the models had different problems, which we found interesting. SQUAD 2.0 dataset is special because it contains unanswerable questions. That means that for some questions, you cannot answer them based on the supplied context, and the aim is to correctly identify those questions as well. In the case of the Slovene model, we predicted those cases too often, but the English model predicted them too rarely. Also, the biggest difference between the Slovene and English models was the multiple choice dataset MC test, where the difference was 33%. We attribute these worse results of the Slovenian model to the machine translations, and also, especially for the multiple choice dataset, to the smaller number of datasets that we use, because in the original work they used 3 additional multiple choice datasets. We tried to improve our results by using cross-lingual transfer, and we used all the previously mentioned Slovene datasets, their equivalents in English, and also 4 additional datasets. Those were narrative QA, race, ARC, and OB QA. Those are all the datasets that were included in the original work. And we found out that the metrics improved on average by 3 to 4%. However, the training time increased 4 times as well. The biggest improvement that we achieved was with the multiple choice dataset NC test. In the end, we also performed a qualitative analysis of the obtained models, and we discovered that the answers are mostly substrings or given choices, and that the models couldn't paraphrase, rephrase, or provide answers in the correct Slovene case. This is also connected to the answers mostly being substrings. The models also had problem with answering multi-part questions where they usually answered to only one part of the question. The task was made even more difficult because some machine translations were unclear or grammatically incorrect. And of course, if even a human has a problem understanding the question, then it's even harder for the computer to do so. In the end, the models were best with factoid questions that required only a short answer. To conclude, our main contributions are the generative unified QA models, which achieve state-of-the-art results for Slovene, but which still lag behind the English results. We also machine translated this additional NCTED dataset, which is available for further work. And for further work, we identified 3 directions which could be used to improve our results. First would be to use better translations or dedicated Slovenian datasets, because the outputs can only be as good as our inputs. The second improvement would be to use larger models and longer training time. This was used in a neural network setting where this usually leads to better results. And also by adding additional datasets. And here we see the most potential in these multiple choice datasets that were improved the most by using cross-lingual transfer, and in the abstractive datasets which would teach the models to paraphrase, and that the answers are not necessarily only the substrings of the given context. Thank you, that would be all, and I will be pleased to answer any questions you have.
Thank you, Katja. I also invite questions or comments.
I don't have much experience with question answering, but when looking at some of the results that you showed, it seems like on some of the problems they're pretty bad. So there was a problem where the baseline was 50%, and this question answering models also gave around 50%. So can you give us an intuition of how well this actually works?
You mean the SKUI dataset?
Yeah, that one kind of.
That one is pretty hard. This is a common sense dataset, which was not our primary focus, but we included it because it was the only dataset that was completely human translated. And here it was the task was to differentiate between 2 hypotheses, which was more probable, and there was some action, and you needed to either find the most probable cause or effect. And also we are still better than the published results, the other published results. So
no, so I'm not trying to say that you're not good enough. I'm just trying to figure out whether this computational question answering is actually useful. And for some of these, it's kind of hard to say whether, I don't know, 0.31 is good or not. I have no idea whether that's good or not. So can you give us an intuition? Does this work, or is it still very immature?
Well, based on, especially on the qualitative analysis, I would say that it is still quite bad, but it is this, there hasn't been much research in this field yet, so I think this provides a stepping stone for further research.
Any other questions or comments?
This is a metric that is usually used for summarizations, and we used it because it was used in the original work. It's something with the recall.
There was another question.
I'm not sure I'm going to phrase this correctly. You say that one of the next steps could be training larger models. Do you think have you already hit the theoretical limits where it still makes sense to increase the parameter count, or are you just trying to grok the models?
Yeah, I think this makes sense because we used only the smallest ones. There are larger ones available, but due to those limitations that I mentioned, we couldn't use it in this work.
Yes, so you mentioned translations. I guess that from Slovenian to English, and then you applied.
From English to Slovenian.
Oh, okay.
Because those data sets are already available in English, but not in Slovenian.
Oh, okay.
There's another question.
Was the neural translation capability separately first? Because if the translations are bad, then it can influence further the question and answering. That was not my main questions. I just want to know, is it possible to maybe combine some of the similar problems? For example, use text summarization, or maybe make sentence predictions to get some question answering? Because in my opinion, there's
Well, that could be something for further research, but I think that the authors of this T5 model, they made some experiments when they tried to combine those completely different tasks, and they found out that it didn't work that well. And about the translations, I said we used two different ways. One was the commercial solution and one was the internal neural translator. And we found out that those commercial solutions were far better. And later on, we translated the whole data set this way, and this data set is also available for further work. But in this case, we obtained the results on the mix of both translations.
Any other questions? I also have a question. So you said that declensions are a problem for these kinds of methods, and yeah, I imagine it's a very difficult problem compared to the English one. So I was wondering, do you have any idea which of the proposed feature work could improve that specific aspect? So with declensions, for example.
I think the best improvement would be to have better translations, because those that were machine translated already the correct answers were not in the correct Slovenian case. So by the models couldn't even learn it because the input wasn't good enough.
So the error propagated from the translation. Okay, thank you, Katja.
Thank you.
Next up is
Dobar dan, moje ime je Martin Žnidaršič, predstavil bom pa prispevek, v katerem smo skupaj soavtorji s Jenijo Polak in Vidom Podpečanom prikazali, kako se da v našem orodju Cloudflows igračkati in eksperimentirati z besednimi vložitvami. Predvsem nas je zanimalo, ali so te stvari dovolj prijazne uporabnikom, ki so nekako neračunalničari, so pa nekako raziskovalci na svojih področjih in jih bi potencialno take reči zanimale. Zdaj smo najprej predstavil platformo Cloudflows, potem bom pa šel na tale specifičen problem in na našo delavnico uporabniki in nekako povratne informacije. Zdaj, Cloudflows je orodje za analizo podatkov in strojno učenje. Takih orodij je cel kup in tipično so razpoložljiva nekako na 4 različne načine. Najprej je večina stvari, večina algoritmov, metod je najprej na voljo v člankih in večina jih tam tudi ostane. Potlej nekatere od teh stvari so implementirane, pridejo v programske knjižnice, dobijo neke API, mogoče celo spletne storitve, se pravi web services, in tukaj jih večina uporabnikov, recimo, ki niso avtori, uporablja na tak način. Potlej nekatere od teh stvari potem počasi pridejo v malo višje nivojske platforme za analizo podatkov in strojno učenje. To so tipično platforme za vizualno programiranje, ki so namenjene tudi drugim uporabnikom. In nekatere od teh stvari se pa vgradijo, se vgradijo v druga softverska orodja, kjer so uporabnikom na voljo na tak način, da oni sploh ne vejo, da se te stvari spodaj poganjajo. Recimo, na YouTubeu tisti sistem za priporočanje uporablja spodaj nek strojno naučen mehanizem in uporabniku ni treba nič razmišljati, kako se ta stvar dogaja. On mora sam veselo klikati in zapravljati svoje večerne ure s tem, da upošteva tale algoritem in ga futra z novimi nabelami. Skratka, ta zadeva nas mogoče malo manj zanima, pa tale tudi. Nas pa zanima tale višjenivojska platforma, takšna je tudi platforma Cloudflows. In tukaj je enih par ovir, ki se tipično pojavljajo za takšne uporabnike, ki pa niso računalničari. Zdaj, prva ovira, ki je zelo huda, je ta, da je treba ponovadi te metode malo poznati. Tu si vemo, da brez poznavanja metod hitro naredimo kakšne nesmiselne reči. To je ena taka ovira. Druga ovira, ki je mogoče malo lažja za jo nasloviti, je problem, da mora imeti uporabnik nekaj znanja ali pa primeren hardware, mogoče mora imeti tudi nekaj znanja o tem, kako naložiti prave knjižnice, zato da bo ta platforma delovala, ali pa da bodo vsi gradniki, ki ga zanimajo na tej platformi, delovali. Se pravi, nekaj problemov z inštalacijo. Zdaj, vse višjenivojske platforme skušajo na tak ali pa drugačen način te stvari malo umiliti, in Cloudflows je tukaj mogoče malo specifičen in je zato zanimiv. Zdaj, kakšne so druge podobne platforme? Takšne je recimo Orange, ki ga verjetno najbolj poznate, to je Slovenska, pač izvira s SKUI-ja, kjer se že dolgo razvija, je odlična platforma, verjetno ena boljših te sorte, ampak takih platform je še nekaj, RapidMiner, Nine, pa še kakšna bi se našla. Tudi Veka je začela biti vizualna in tako naprej. Zdaj, te platforme so precej podobne, vse imajo neke tipične elemente, vse imajo neko platno, neko belo površino, na katero stavimo stvari, gor postavimo gradnike, se pravi neke softverske komponente, ki jih med sabo povežemo tipično na tak način, da po teh povezavah tečejo podatki, se pravi iz izhodov enega gradnika v vhode drugega in tako dalje. Zdaj, Cloudflows je tudi take sorte platforma, ampak je malo posebna. Posebna je v tem, da teče v brskalnikih, se pravi je spletna platforma. Deluje v brskalnikih, ni potrebno ničesar inštalirati, nobene namestitve na strani klienta ni zahtevane in tudi vse, kar se izvaja na strežniku. Se pravi, vse zapornije, vse knjižnice, ki jih neke posebne komponente zahtevajo, so že nastavljene in tečejo na strežniku. Zdaj, podobno kot vse platforme, ki sem jih prikazal na prejšnji prosojnici, pa ponuja to vizualno programiranje in izdelavo delotokov, svojih workflowov kot rešitev. Zdaj, ker je spletna platforma, je tudi rezultate zelo enostavno deliti, mogoče za razliko od ostalih. Se pravi, bom prikazal kako, ampak zelo enostavno lahko, ko enkrat pridemo do neke rešitve, zelo enostavno naredimo javno, zelo enostavno jo razpečujemo, ne, in delimo z ostalimi. In ti ostali potem tudi zelo enostavno lahko to rešitev poženejo znova, ponovijo naše eksperimente mogoče, ali pa jo skopirajo in nadgradijo, tako da naredijo nekaj po svoje. Vseeno je pa Cloudflow raziskovalni prototip, tako da marsikaj pa ne deluje idealno. Jaz bom seveda danes povedal in prikazal, da je vse odlično in imenitno. Seveda v praksi, če greste poskusiti, kakšna stvar tudi ne deluje, ne deluje prav vedno. Ampak uptime je kar presenetljivo dober. Zdaj, stvari v razvoju že kar nekaj časa, na IS že od leta 2010, se pravi kar več kot 10 let, in glavni razvijalec je bil večino časa Janez Kranjc. Največ časa je bila živa verzija 1, se pravi običajni Cloudflow, a pa temu, kar zdaj rečemo Cloudflow 1. In ta je bila v prvi vrsti namenjena temu, da smo želeli narediti neko platformo, kjer bomo lahko ponavljali eksperimente, in v drugi vrsti, kjer bomo lahko programsko integrirali stvari na projekt. Se pravi, tam smo skušali uporabiti to platformo tudi zato, da smo jo nekako uporabili kot integracijsko platformo za nekako tako, recimo, blago integracijo na projektih, kjer bi vsak partner razvil svoj programski gradnik. Ta platforma bi bila pa uporabljena kot integrator in hkrati za diseminacijo tako prikazanih rešitev. In to je precej dobro delovalo. Imeli je tudi nekaj izpeljank, TextFlows, ki je bil posebna izpeljanka za analiziranje tekstov, ConcreteFlows, ki je bil namenjen rešitvam z področja računalniške ustvarjalnosti. In tudi pri teh, predvsem pri ConcreteFlows, je bilo zanimivo, da je precej partnerjev bilo sposobnih tudi ustvariti svoje lastne gradnike za tole platformo. Zdaj, zatem je prišla druga generacija, v kateri smo skušali rešiti en kup težav, ki so se nabrale. Med drugim to, da je bilo zelo težavno med gradniki prenašati večje količine podatkov, ki je bila potrebna za tako izvajanje, ampak ta druga verzija nekako nikoli ni prišla do javne dostopnosti, nekako smo prekinili s tem razvojem in naredili pa novo Cloudflows 3, za katero je bilo predvsem značilno, da je imela ločen front-end pa back-end, se pravi to ozadje in spredje, in je omogočilo tudi nekaj par naprednejših reči, recimo shranjevanje vmesnih rezultatov, s čimer smo lahko začeli delati tudi z malo večjimi podatki. Zdaj, za to verzijo 3 je značilno, da ima kar precej gradnikov za obdelavo naravnega jezika, zato ker je nastajala vzporedno z evropskim projektom Embeddja, in to je različica, ki je trenutno razvijana in podprta. Razvijalec je pa dr. Vid Podpečan. Zdaj, Cloudflows je odprto kodno orodje, se pravi, kot sem že omenil, na voljo je na spletu, če greste tukaj na cf3.is, dobite pač vstopno stran platforme, ki je gostovana pri nas, na naših strežnikih, in se lahko registrirate in jo uporabljate. Če pa kdo želi, si pa lahko celotno programsko opremo pobere z GitHuba tukaj in naredite svojo različico platforme, jo gostite pri sebi in naredite svojo nekakšno verzijo, ki jo potem lahko tudi nadgrajujete. Zdaj, zakaj bi človek to počel? Ni prav zelo priporočljivo, ker ni toliko enostavno, kot samo uporabljati kot navaden uporabnik. Je pa mogoče zanimivo za koga, ki bi hotel imeti platformo za kakšne stvari, ki so občutljive v smislu varnosti podatkov. Se pravi, če bi kakšno podjetje hotelo tako platformo imeti za interno rabo, si lahko to namestite. Zdaj, pri Cloudflows nas najprej pričaka začetna stran, ki izgleda takole. Pravi, lahko poskusimo en kratek interaktivni priročnik, lahko pregledamo workflowe, se pravi te delotoke, ki so jih ostali naredili, pa so jih javno delili, lahko pa gremo izdelati svoj nov workflow. Zdaj seveda zato, da bi lahko to začeli uporabljati, se morate prijaviti, ampak ne poberemo prav dosti podatkov, tako da prijava je precej enostavna. In potem pridemo do tega glavnega pogleda, ki tudi ni prav zelo različen od ostalih platform, se pravi imamo tole platno, imamo programske gradnike, tako imane widgete, ki jih vlečemo sem gor in seveda povezujemo zadeve izhode na vhode. Ne? Tukaj pri Cloudflows imamo zelo preprosto narejeno, da vsak takle moder kvadratek je nek vhod ali pa izhod v programski gradnik. Spodaj imamo pa še, zato ker je to pač raziskovalni prototip, ne, imamo še področje, kjer se sporočajo lepi, zeleni, uspešno izvedeni rezultati, pa tudi napake, kadar se zgodijo. Zdaj, če želimo tako narejen workflow pognati, lahko pritisnemo tukaj play, pa se požene v celoti, lahko pa tudi gremo na posamezen gradnik, pa poganjamo workflow po kosih, recimo do neke veje. Ne? Recimo, če bi šli na ta gradnik tukaj, ne, bi se pognali samo te stvari, ki so nujne, zato da se ta stvar izvede. Ne? In podobno, kje druge. Skratka, lahko poganjamo v celoti ali pa po koščkih. Kot sem omenil, je zelo enostavno deljenje že izdelanih rešitev, ne, se pravi takih workflowov. In tudi tukaj Cloudflows ni prvi. Ne. Eden prvih je bil portal My Experiment, to je ena taka iniciativa, tam je bilo precej zelo zanimivih workflow deljenih že del časa, to je že precej stara zadeva. Tam so večinoma delotoki orodja Taverna in podobnih. Mogoče za nas je malo bolj poznana iniciativa OpenML, tam mogoče niso prav delotoke, ampak so tudi ostale reči deljene, ampak OpenML je res čudovit, ker ima precej meta podatkov, tako da ima precej zelo zanimivih reči in omogoča zelo napredno deljenje svojih rešitev. Kar pa ne omogoča pa tega, kar Cloudflows ponuja. To je pa, da poganjamo, delimo z nekom povezavo, človek potisne gor, požene svojo verzijo in tako lahko zalaufa in ponovi rezultate, ne, brez inštalacije. Skratka, to je omogočeno s tem, da se zadeve izvajajo na strežniku. Če so zadeve zelo zahtevne, nam pomaga tudi nekaj pristopov za paralelizacijo, ki teče v ozadju. Kar pa je težava, je pa prenos podatkov. Ne. Se pravi, zato, ker zadeva teče pri nas na strežniku, če imate ogromne podatke, ja, vse te ogromne podatke bo treba prenesti. Ne. In vsaj v nekaj fazah se ti podatki prenašajo tudi med temi gradniki, čeprav lahko zdaj v tej novi verziji to zadevo vmes shranite vmesne rezultate v bazo. Zato, da naslednjič, ko poženete, da te zadeve tečejo naprej. Zdaj, deljenje je zelo enostavno rešeno z enostavnim URL naslovom. To je spletna zadeva. Tukaj imamo pogled deljenja workflowov. Ko imamo nekaj stvari narejenih, gremo na tale Your Workflows in tukaj nam recimo pokaže workflowe, ki jih imamo. Mogoče so nekateri poimenovani, nekateri ne. Za vsakega pa imamo nekaj opcij. Lahko ga editiramo, lahko ga odpremo kot novega, to bo naredilo kopijo workflowa. Lahko ga izbrišemo, eksportamo v JSON, samo definicija se bo prenesla v JSON format. Lahko pa ga naredimo public, to pomeni, da bo ta workflow ne bo več samo naš, ampak bo postal javni workflow. Če kliknemo make public, se zgodi to, kar se je zgodilo pri tem od spodaj, da dobi workflow svoj URL. Ta URL enostavno lahko skopirate, prilimate v članek ali pa pošljete po mailu in vsak drugi uporabnik Cloudflows lahko klikne gor in ga uporablja svojo kopijo, kot da bi jo naredil. Seveda, kadar je ena stvar public, se ta zadeva spremeni tukaj v make private, se pravi, vsako tako zadevo lahko spet privatizirate. Tukaj morate biti edin previdni, da ko nek workflow naredite, da je public, to velja tudi za vse podatke, ki tečejo. Ker kadarkoli lahko nek uporabnik vmes postavi nek widget in podatke, ki so noter shrani v tak gradnik ali pa da bi se sredi. No in ko so workflowi v javni rabi, se pojavi avtomatsko na tele strani Explore Workflows. Spravi, čim sem ga jaz naredil, ta workflow, da je public, se je pojavil tukaj in pove, kdo ga je naredil, kratek opis in vsi ostali uporabniki Cloudflowsa imajo na voljo ali dobiti URL, zato da ga delijo naprej, ali pa ga zalaufati kot svojo kopijo. Zdaj, jaz imam pa opcijo ga tudi editirati, zato pa ostali ne bi. Če gremo zdaj k tem tekstovnim vložitvam, gremo najprej s tekstom povezane gradnike. Precej jih je, tukaj sem par najbolj uporabnih. precej takih, ki so namenjeni vnosu podatkov, glih zato, ker je namenjeno ne računalnikarjem, da čim lažje vnesejo podatke, pa tudi precej takih za delo s tokeni, filtriranje, frekvence, lematizacija, take tipične operacije, ki se delajo na tekstu. Zanimivo je, da imamo lematizator, pa še tudi kakšne druge stvari prilagojene tudi za slovenščino, pa tudi za kakšne druge jezike iz naše soseščine. Se pravi, če delate s temi jeziki, mogoče fino se tudi tukaj kaj poigrati. No, vektorske vložitve so pa enostavno predstavitve besed z vektorji, se pravi, predstavitve besed ali pa daljših tekstov v vektorskem prostoru, kjer ne bi veljalo, da so pomensko podobne besede blizu, vsaj v praksi tiste besede, ki se nahajajo v podobnem kontekstu v tekstih. In verjetno veste za vse te opcije, ki jih to omogoča, se pravi, poleg tega, da je taka predstavitev zanimiva za razne naloge, kot je klasifikacija in tako naprej, ali pa samo za pregledovanje sosednosti, ki je predvsem bolj enostavno, se da celo računati s temi vektorji, se da pogledati takšne, ta je tipičen primer, king minus man plus woman je tipično queen. Dostikrat je pa tudi malenca, samo tu v primerih ne boste videli. Skratka, več je pristopov, kako pridemo do teh vektorjev. Eden od najbolj zanimivih je fast text, ki besedo nekako razbije na več engramov, se nekako zapelje z enim okencem po besedi in vsak tak engramček posebej zakodira. Prednost tega je, da je uporaben na besedah, ki jih ni v učni množici, Twitter, ampak je podobnega, ki ima besede z napakami in rezultate ima dobre tudi na morfološko bogatih jezikih. Prej smo slišali, da takšen jezik je kot slovenščina, pa ti jeziki, ki so v naši bližini. Slabosti pa so, da je malo počasnejši od enostavnih pristopov in ni toliko dober, nima toliko fascinantnih rezultatov, kot pa res modeli BERT in podobni, ki so še precej zahtevnejši. No, seveda v Cloudflowsu imamo kup prednaučenih modelov, se pravi, modeli so bili že narejeni in nam samo naredijo take vektorske predstavitve. Kar je pa bolj zanimivo pa je, da smo v primeru fast teksta naredili tudi gradnik, ki omogoča učenje vektorskih modelov. Se pravi, da se naučimo to na lastnem korpusu. Seveda, to je vseh nekako interaktivno, pravi v nekaj sekundah samo za take stvari, ki so do 2 milijona besed, 10 mega golga teksta približno. Skratka, kakšne Moby-Dick, kakšni romani, 10 brat Moby-Dick, to gre v sekundi, dveh, Biblija se že malo načaka, več kot toliko pa človek ne ve, če boste mogli pač počakati svoje izmelje. Imamo pa tudi par posebnih widgetov za delo s temi rezultati, se pravi, lahko pogledamo sosednje besede, lahko evalviramo tele vektorske izraze, če bi hočeli. In imamo tudi par drugih widgetov iz projekta Embedian, ker danes ne bi kazal. Tako da bi za konec sam še povedal o delavnici, ki smo imeli z uporabniki, se pravi dejansko s takimi uporabniki, ki niso bili računalničari. To so bili večinoma strokovnjaki z področja humanistike, literarnih ved, se pravi strokovnjaki na svojih področjih, ki pa niso bili programerji. In mogoče in kakšni taki elementi niso zelo znani. In predstavili smo jim, kako se da malo eksperimentirati s temi vektorskimi predstavitvami in kako se da pogledajo na nekih svojih korpusih, kakšne so sosednje besede. Delavnica je izgledala tako, da smo imeli najprej uvodno predstavitev, Vid je čudovito predstavil Cloudflows v 20 minutah, potem smo pa vsakemu posebej nudili 20 minut nekako priložnost, da nekaj svojega poskusi in če je človek zašel težave, smo mu pomagali. Tipične težave so bile format teksta, kodne tabele, tukaj je bila tudi ena skoraj najrešljiva, ne UTF kodne tabele teksta s čudnimi znaki, tudi lingvisti, kot hitro imajo take zelo čudne reči, na katere mi niti ne pomislimo. Tako da, imeli smo en tak workflow, precej preprost, ker smo naložili tekst, imeli smo en tokenizer, lematizator za slovenščino in potem so tukaj naučili svoj fast text model na svojem korpusu in potem pogledali enih par sosednjih besed ali pa evalvirali rezultate takih izrazov vektorskih. Tukaj rezultati niso bili posebej za domov pisati, Tle je bilo dostakrat king minus man plus woman valencana, ne? Oziroma v tem smislu, ampak to je zato, ker so bili ti korpusi relativno majhni. So bili pa ti korpusi zanimivi, no? To je bilo res zanimivo gledati, tudi nam, ne sam njim. Oni so bili zelo pozitivni, po mojem, zato, ker je videti tako lepo predstavil pa jim prijazno pomagal. Ampak so imeli res zelo zanimive probleme. Ne? Od tega, da so imeli romane iz dveh različnih obdobij, do tega, da so primerjali dva različna avtorja ali pa dve skupine avtorjev. Tako da meni so čuda takih stvari, ki sploh ne bi pomislil, da bi jih človek počel. No? Skratka, mi kar prav prišlo. In kar je bilo še ena zanimiva stvar, ne? Da so jih zelo zanimali zelo preproste operacije, ki nas sploh ne brigajo. Ne? Recimo, v korpusu kakšna je frekvenca besed, ko posortirati. Katere besede so najbolj pogoste. Pa vidijo, kaj je, so hitro videli, da teme ne zanimajo, ok, a se da sfiltrirati, ja seveda se da, ne. Pa sfiltrirati, pa spet frekvenco pogledati, wow, ne. Skratka, stvari, ki so preproste, ne, ampak logično, ne, če človek ne zna tega sprogramirati, če ne more, je težava, ne. Tako da, to je bilo res lepo videti, no, kako take, tudi preproste reči, hitro dobijo zelo dobre ideje, kaj s njimi početi. No in glavni feedback pa je bil, no, ki je pa nas zanimal, a bi še uporabili Cloudflows, ne. Večinoma ste rekli ja, ne, zato ker so bili tam, pa smo jih mi vprašali, sicer čez nekaj časa, z anonimnim vprašalnikom, ne, ampak vseeno, ne. Po mojem so bili malo pozitivni tudi zaradi tega, čeprav je bil anonimni vprašalnik, predvsem pa so rekli, če bi imeli na voljo delotok za svoj problem, se pravi, kljub temu, da smo mi razložili, kljub temu, da smo mi mislili, da je Cloudflows enostaven, očitno ni to zelo enostaven in je treba kakšne take stvari predpripraviti, potem pa se znajo igrati in znajo dopolnjevati in imajo ideje. Ne. Tako da zaradi tega smo tudi mi malo fokus, bomo začeli spreminjati in bomo malo nehali z razvojem in mogoče malo začeli bolj z pripravo specifičnih rešitev, zato da bodo tudi ti uporabniki z njimi kaj počeli. To je vse, kar sem hotel povedati. Hvala.
Vabljeni k vprašanjem ali komentarjem.
Kakšni bi bili pa kakšni od njihovih problemov, ki jih preprosta orodja ne rešujejo, ampak bi jih to orodje rešilo, katera bi bilo recimo en tak problem, ki je najbolj pogost?
Recimo te vektorski sosedi, ne, besed, ne. Kaj so sosednje besede po pomenu glede na nek korpus, ne. Recimo, tukaj imam en demo, ne bo časa, ga kazati, ne, da sem že kar do konca časa. Če primerjamo besedo kri v vektorski sosedščini romana Moby Dick ali pa Dracula, so zelo druge besede pridejo kot semantično podobne oziroma da ne bi se na istem mestu pojavljale. Ne. Tako da to je ena taka stvar, ne. To je še kar recimo zanimivo. Je pa res, da ja, bolj mi je bilo všeč res te frekvence in filtriranje.
Se pravi, niso že sami prišli k vam s problemi, ampak ste vi predstavili nek nabor.
Ja, mi nismo niti povedali, kaj bodo videli. Mi smo rekli, imamo neko orodje, povabili smo jih, vedeli smo, da so to ljudje, ki imajo neke korpuse. Rekli smo, pridite z enim korpusom in boste nekaj poskusili. Noben od njih ni imel nobene izkušnje s Cloudflows prej, zelo malo tudi s podobnimi platformami in enostavno so imeli neke korpuse, na katerih so delali. In so pol imeli pač te začetniške težave, unesti, pogledati, pa smo skupaj malo gledali, kaj je noter. Kakšne stvari so bile zanimive, no? En je bil zanimiv ta korpus teh tekstov o LGBT tematikah iz različnih obdobij, mislim, da je bila tam zadeva. In so bili spet tile frekvence, kakšne besede se tam pojavljajo včasih, pa kakšni so včasih. Nekaj časa nazaj, pa zdaj, tako zanimivo, pa kakšne sosednosti, ne? Kakšne so kvazi, so pomenke nekaterih reči. To je bilo kar zanimivo.
Kakšno vprašanje?
Korpusi so tudi na voljo že kakšni v sistemu, ne?
Prav dosti jih ni.
Okay.
Tele javni delotoki imajo ponovadi kakšne zelo varne korpuse. Kakšne te romane, ki so že brez licence, ne, Deseti brati, pa kakšne angleške korpuse, pa nekaj korpusov novice, no, ki so večinoma tudi pobrani iz kakšnih javno dostopnih reči. To, kar je tam v teh javno dostopnih delotokih, so večinoma zelo take, že tako ali tako javno dostopne zadeve. Ni nekaj, kar bi bilo novega, po mojem, ne vem pa kaj. Ja, se tudi kdo zmoti.
Kakšno vprašanje? Ja, sicer pa hvala. Predstavitev bo naš, izvoli.
Hi everyone, my name is Ilya Soynik and I'll be presenting joint work with myself, Bernard Jenko and Martin's leadership that we did in the scope of the Resilog project on social media analysis for assessing resilience. So I think the first thing that would be fair here is to explain what resilience is in this particular context or how we were asked to analyze it. And we're going to start with this UN definition where resilience is the ability of a system, community, or society exposed to hazards to resist, absorb, accommodate, adapt to, transform, and recover from the effects of a hazard in a timely and efficient manner, including through the preservation and the restoration of its essential basic structures and functions through risk management. So what this essentially means is that we want to make a society or a community less prone to not specific disasters, but less prone to bad management of disasters or extenuating circumstances that will, after the fact, make these worse. An example of this would be, for example, the nuclear reactor leak in Fukushima, which itself wasn't all that bad, but then the handling of the entire problem actually made it much worse. So this is where we come in through the Resilog project. The Resilog project is a Horizon 2020 EU-funded project. The name stands for Resilient Europe and Societies by Innovating Local Communities, just to make to fit the acronym, obviously. But what the Resilog project mainly aims to do is to improve the resilience of local communities, and this is done through two main ways. The first is the organization of local resilience teams, or LRTs for short, which are teams that are in charge of assessing the resilience of a particular community. These are usually made up from members of civil protection agencies and are intended to work in a specific location in a specific community. And the second thing that Resilog aims to achieve is to provide these LRTs with a unified platform that contains a semi-automatic toolset which allows these teams to assess the resilience of their communities. Now, this is done through dimensions, indicators, and proxies. And how this looks is basically like this. We have 6 dimensions, which are represented in the inner circle: infrastructure, environment, governance, economic, social, and I think I forgot what the last one is. But anyways, each of these 6 areas, dimensions, is assessed through indicators, which are basically sub-dimensions. There's a word that's escaping me right now, but anyways. So we divide these broad areas into smaller ones, which are indicators, and then these indicators are still fairly general, and these are then approximated by proxies, which are some values that are calculable. So how this works is we say, oh, I don't know, this is the social dimension is then divided into trusted to the authorities, and then this is further divided into, I don't know, the percent of people that attend local elections. And The last one is entirely calculable. It's just, it takes some numbers, you calculate it, whereas the social dimension as a whole is a fairly broad concept. But this allows us to get a good assessment of the resilience of a local community. How this works is that an LRT would use the platform, they would select which of these they want. All are not relevant, all indicators are not relevant for all communities, so they would be able to select the ones that are, and they would get this kind of Rosetta, which is an assessment of the resilience of a community at a given time point. And then at a later point, they could say, oh, let's try this again. The proxies get recalculated, and maybe we can see that they have started failing in one of the dimensions. The colors would turn first orange and then red, because we all know red is bad. And then this might look like there's one bad one there. And this might look much more dire. This one is an example of a fairly good resilience of a community. So where do we come in? Well, our idea was, let's do some social media analysis and try to provide some way to assess the proxies, either to be used directly as the proxies in the system or as part of the calculation of the proxies. So originally we were looking at Facebook and Twitter data, but in the end it turned out that Facebook is a bit too restrictive in what you can access. So we actually use Twitter data because their policy actually allowed us to have easy access for academic and research purposes. We wanted to look at the tweets and within them identify topics that were related to resilience. And finally, we would look at how the public sees the topics related to resilience by using sentiment classification. So if we get positive sentiment on resilience-based topics, the public seems to be aware or is happy with the operation of with the resilience of the local community. And then once we've done all of this, we can provide some aggregates and visualizations that could be used as proxies within the Resilo platform. Now, here, the idea initially was for these to be used as proxies directly, but in the end, there was some fear of over-automation. So this was still used by the main experts as a step in calculating the values of the proxies. So we used a fairly straightforward data pipeline to achieve this. We started with data collection, which was done through the Twitter API, by just selecting tweets based on the communities that were involved in the project. This means that, for example, Gorizia was one of the communities that was involved there, and we just said, okay, let's get all of the tweets that mention Gorizia as a keyword. In the end, we only had 2 communities involved here that had a sufficient volume of tweets for the analysis to make sense. This was Gorizia at the Slovenian-Italian border and Catania in Sicily. Then we did some filtering and cleaning because it turns out that Gorizia and Catania are both names of some celebrities or used in this context as well, which means that, well, this is not really something we're interested in. We also filtered the language to Italian and so on, because the classifiers that we use later were based on Italian. And then we did some data segmentation. Now, what was interesting here of interest to us was that we wanted to see how this would change. So we wanted to have data that would span different time periods. And here we actually looked at monthly and yearly reports, and we did this topic modeling, which would allow us, ideally, to extract the tweets that were related to resilience. And then we did classification, because this is some of what we do. And we used 2 different classifiers, the logreg classifier, which was developed in-house at our department, and the Philip classifier, which is a publicly available classifier, sentiment classifier for Italian. Finally, we provided some aggregates and visualizations through a fairly simple web application. So what are the interesting steps here? The interesting step is topic modeling and classification, and then maybe the web application, which hopefully I'll have time to show the demo for. How did we go around about topic modeling? We said, okay, let's try something fairly standard. We use LDA or latent Dirichlet allocation, and let's just extract a fixed number of topics based on word co-occurrence, basically, right? Turns out there's not enough tweets, or mainly there's not enough tweets specifically related to resilience for them to identify as a separate topic. Maybe this would get subsumed into a larger topic about civil infrastructure or civil governance, but it turned out that the topics that we would mostly detect were really big things like sports, or in some cases, in this case that we get to later, it's during COVID, there was in Gorizia, the border crossing was fairly contentious because of different pandemic situations. So there was a lot of tweets based on this, but other than that, topics were really not resilience related. So what we ended up doing, we said, okay, this is not really working. We're just going to get our domain experts, our local community members, to define the topics that they want to see. And this is done through providing a set of keywords or tokens that need to appear in tweets for them to be considered a part of this topic. The next thing that we did was sentiment classification. So we have these two classifiers. The first one is called logreg. It's based on the logistic regression. It's done for Italian. It's implemented in Python. The code is available on this URL. I'm not going to go into details because this is not really the point. The other one, again, is the publicly available one. Well, both are publicly available. This one's available from elsewhere. It comes also actually as a Python package, which was fairly nice. It makes it really easy to use. It's available at this URL, and these are the appropriate citations for them. I'm really trying to get to the interesting bit, which is the demo. So finally, we have a really lightweight Flask Unicorn Webster, which is running in a Docker image in a server somewhere over there, probably. And we did some visualizations with Apex charts. Now I'm done with my slides. I'll switch to the demo because I think it's going to be much more interesting. Do this. All right. So right now we're not seeing anything because I'm not really. Which way does this go? No, either way. Because I haven't set input the security token, right? We only want the users to be able to see the data that they have clearance for. So right now I'm just going to enter the security token, which was created specifically for presentations, which is the demo token, and this actually allows us to see how this works. So for this demo, we have some data spanning from start of 2020 and the end of 2022. We are not doing black magic. We're not looking into the future, but these reports are just there as stand-ins for when the data will actually be available, because it allows us to do some prettier visualizations. We're using the affiliate classifier for this one, and then we can look at how, let's say, a particular report looks. So we have the number of tweets, how the sentiment is distributed into positive and negative. We can see here it's more or less half and half. We have some tokens that frequently occur in these tweets in this particular month. You see that we have some positive tokens. Slovenia is positive in Italian, apparently, at least in Gorizia. Elsewhere, especially now, might be different. And some negative ones. And then these are the values. Here they're called indicators. They shouldn't be. They should be called something else. But these are the things that we want to provide to local resilience teams as some concrete values, calculated values that they can then use to assess what is the community perception in this particular case. Now this is the broad one, and then further on we can get into the topics. These are just what's the ratio of positive tweets, negative tweets, how the volume has changed from the previous time period, both relative and absolute. And then this is the interesting bit, are the topics. Here we get a similar view for the topics, and we can see what are the keywords that define this particular topic. And this is a COVID-related topic that was requested by the domain expert, and it has vaccines, COVID, virus, and so on, lockdown, mortality. And we can see that here the sentiment is predominantly negative, skewing to about 2/3 negative, whereas the entire tweet collection was half and half. Some other topics, and we have quarantine, so on. So this is sort of the standard view, but if we go back, the yearly view is maybe a bit more informative. So let's go to yearly view. And this one actually sports some extra visualizations. Here we have relative sentiment through all of the months in 2020, where we can see how the amount of positive tweets increases towards the end of the year. People are getting happier for the holiday season, I suppose. This is not tested, I'm just guessing. We also have this graph in absolute values, so we can actually see that the volumes of the tweets are actually not static. So we're saying something like that is like commenting on just, people getting happier is maybe, oh no, they're tweeting more, they're tweeting less. So this is how we present this so that we can give the local teams as much information as possible. And we have these yearly views for our topics as well, right? And we can see that during the start of 2020, the sentiment was mostly negative in this COVID related, and then it started trending a bit towards, well, maybe equal-ish as the disease was getting more researched. There was maybe signs of a vaccine and so on. We can also see, obviously, in March, there were the most tweets about COVID. Makes sense, right? I mean, this is a fairly sizable community, and we still only have like 600-ish tweets in a month for COVID. Now, if we did this on a larger community, sure, we get better data, but then it also becomes a question of how useful this is for thousands and thousands of tweets, because the community is not that large. At least it's not, the size of the community was not targeted to be as large in Resilog. Finally, maybe I'll just show this, how the users can request new topics. You can say, oh, we want this new topic, please provide it for us. The process of data collection and aggregation and so on is fairly time consuming, so this needs to be done manually, so this can't run automatically. So we've provided a form where the local teams can say, oh, please add this topic for us. So we would just separate some tokens that we can then filter and run all of our machinery on. So that's it for me. If there's any questions, now's the time to ask them.
Thank you, Anish. Thanks. Does anyone have a question?
How many people, in these regions are actually using Twitter? Because it's like not very common here in Europe and stuff, right?
Yes, and that's one of the problems that we encountered from the start, is that we had, was it five communities, and then only 2 of them even had sufficient amount of tweets for us to do this. So this is more of like, we kind of made it a general tool set that you can use, but you need to know when to use it, and that's when the volume of tweets is high enough. But yes, this is not a one-size-fits-all solution, because running analysis in 5 tweets is not going to tell you anything.
Is there like, do you like have any ideas about like some other sources for this data that could also be used, except for, let's say, Facebook, which is complex to get anything?
Well, one of the initial ideas was either news or comments on news, but that turned out, at least within the scope of the project, was considered a bit too complex or too, say, fiddly to work. Twitter's API is very nice to just say, I want this from this time period to this time period containing these words. That's it. So our role in the project was fairly small. So this was well, the extent of what we did. There were some ideas for extra stuff, but we didn't get paid to do it in the end.
Unfortunately.
Yeah.
Any other questions?
I kept seeing the neutral sentiment in the legends of the visualizations, at least, but never on the charts themselves.
Yes. So this is as a result of the field classifier. Field classifier only classifies tweets as positive or negative, whereas the other one, the logreg, which I can show because we don't have prepared for the demo, actually has a third option of neutral sentiment. So in this case, yeah, the visualizations are a bit, well, bare because they only have 2 classes, but we do also support this third option.
But when you use the other classifier with 3 options, what's the distribution like? Is neutral?
Oh, there's a lot of neutral tweets. Yeah. There's actually, most tweets fall into neutral or negative with, well, the classifier is fairly conservative with positive tweets. For, let's say, the label data didn't contain that many positive tweets. And let's be honest, Twitter is not a place where people usually go to express positive opinions. So I think that's realistic to some extent, anyway.
There was a...
How do you deal with the retweets, and are the tweets from influential people?
No, we didn't do any kind of social network analysis in this case. We just give me these tweets. We deal with retweets in the same way that the API deals with retweets, which I don't think we get them at all. Or were they filtered out? Oh, we do? Okay, so we do get them. Martin was doing the data collection, so.
Okay, I think we've run out of time. Thank you, Aljaž. Now it's time for the let's hit the one.
Indeed. So, as we've done over the last few years, we have selected the best paper of the conference. I'm happy to say that this year we've done it a little bit more thoroughly than in the previous year, so the winner can be more sure that they're really good. In the end, the whole program committee was invited to vote on the best paper out of the select few candidates. And this paper is IMF Quality Assurance of Mammograms Using Deep Convolutional Neural Networks and Transfer Learning by Gaspar Sapničar, Peter Us, Erna Alukic, Nejc Mikiš, Miha Mlakar, and Janez Živer.